Welcome to our course in Introduction to Physics-Based Animation. My name is Tamar Shinar. I am at the University of California, Riverside, and my co-presenter today is Adam Bargteil. He's at University of Maryland, Baltimore County. So today we want to give you a brief introduction to a lot of the fundamentals of physics-based animation. So this course is geared towards people who don't have much of a background in physics-based animation and want to get started, want to get an idea of sort of the landscape of the methods and the problems. And it's going to be quite introductory. So with this, I'm going to pass it over to Adam.
Hi, happy to be here. So let's get a simple start with particle dynamics. And we'll just jump right in and consider the problem of tracing a particle through a velocity field. So here we have a velocity field, and here we have a particle. And that particle is going to follow the velocity field and end up at some position. And here we have another particle, and that particle is going to also flow through the velocity field, but it ends up at a different position and it follows a different path to get there. We can describe what's going on here using what we call an initial value problem. It's an initial value problem because we have an initial value. The position of particle x at time 0 is equal to some x0 that's given. And then we have the derivative of the position. We have a function for that, and that's the velocity field that we're following, v. So when we're talking about derivatives, what we're really talking about is change, and change is related to difference. And so we actually call this a differential equation. It's an ordinary differential equation because we have no partial derivatives, we just have regular derivatives. And it's a first order differential equation because we only have a single derivative with respect to time. This is a nice place to start because it's simple, it's powerful. Actually, a lot of techniques rely upon this simple operation, this simple equation. And it's also really instructive. We can learn a lot about physics-based animation and numerical computing just from this very simple example. So the first method to solve this is Eulers Method. And so we'll look at how you get to Eulers Method. So we start with the formula for a derivative that you probably remember from your first calculus class. We have the change in x with respect to time is equal to the limit as epsilon approaches 0 of the difference between the position of x at time t plus epsilon minus the position of x at time t divided by our epsilon. Now in order to do this with a computer, we can't actually solve with a limit as epsilon goes to 0, so what we do is we set epsilon equal to some delta t, some small number. And we can rewrite this as the approximation to the derivative of x with respect to time is going to be what we see on the right-hand side. Now we do a little bit of rearranging, and we take into account that we know that the derivative with respect to time is equal to the velocity. This gives us that the right-hand side of the first equation is equal to the velocity. Do a little bit of rearrangement, and we get this formula for how to update the position in time. So we have that the position at time t plus delta t, some short time in the future, is equal to the old position times plus delta t times the velocity. So at this point, we can talk about the big trade-off in all of numerical computation. So we have this approximation here. As delta t decreases, the approximation gets better. But the computational cost increases. So we can always pay more computation cost to get a better approximation. And we can always save computation cost if we are willing to accept a less good approximation. Let's consider another problem. So in the real world, F equals ma. This is one of Newton's laws of motion. And so we can have another initial value problem where we have the initial position. And now we have that the second derivative, the acceleration of x with respect to time, is equal to the force that's acting upon x divided by the mass. This is a second order ordinary differential equation because we have a second derivative with respect to time. We can recharacterize this same initial value problem by introducing the velocity. And so we have that we specify initial positions and velocities for our particle. And then we have a derivative for the position with respect to time, and then we have a derivative of the velocity with respect to time. And so these are first order derivatives, and so this is a coupled first order differential equation. And if we use Euler's method again, we get a very similar formula to what we had before. The position in the future time is going to be the old position plus delta t times the force divided by mass. And we have the same exact update to the position. And this is known as symplectic Euler. It happens to be a really good integrator. If you need to integrate some second order system on the weekend, this is the one I recommend. We can actually code this up in just a few lines of code. So we create a little particle class or structure with a mass, a position, a velocity, and a force accumulator. We initialize all the forces to 0, and then we loop over all the forces in our system. And then for each particle that's affected by that force, we add that force to the particle. And then we have another loop over all the particles, and we integrate forward in time by updating first the position, and then, or first the velocity, and then the position. And all particle effects are basically done like this. We come up with some forces that we want to act on our particles, and then we integrate forward in time. And I encourage you to check out Carl Sim's Particle Dreams. ACM permissions don't allow us to actually show it to you, but you can see it on the internets. And it's one of the first examples of particle systems, the simple dynamics actually being used to create some really nice visuals. So now let's add springs to our system. So the classical formula for a spring, F equals minus kd, this is a Hookean spring, where F is the force, K is some constant that says how stiff our spring is, and D is the displacement, how far the particle is from 0. And using our notation, we would call this Fp is equal to minus K times Xp, because we were using X to define our positions. So then we can think about, what if we want a non-zero rest length? Well, in that case, we can rearrange things a little bit and introduce the length of xp. And so the very last term on the right there is just the direction of xp. And then we have the length of xp in the parentheses. And then we can bring in a rest length r. And so now we're measuring how far the length of xp is from the rest length that we're shooting for. It turns out, though, that formulation isn't that great, and it's better to use what we call a strain metric. And so here, a strain metric, we take the xp, the length of our spring, and we divide it by the rest length. And by taking the length of the spring and dividing by the rest length, we now have a dimensionless quantity. We're taking meters and dividing by meters, and that gives us something that's dimensionless. And so a dimensionless measure is a good measure of strain because now k doesn't depend on how long the rest length was. K is an independent material property. And so when we rewrite our formula for the force, we get something that's simply the K, which is a user-specified stiffness, a strain metric that tells us how much our spring has either been stretched or pushed together, and then the direction that the particle should move to change the length of the spring. So we have that formula. What if we want an arbitrary connection point rather than connecting to 0? Well, to do that, we introduce another particle, xq, and now the length of our spring is going to be xq minus xp, and the direction that we want to move is towards xq. And so we get a formula for force that looks like this, and then fq is equal to minus fp because we have equal and opposite forces. We can also introduce damping. In order to introduce damping, we get a little complicated here. So we have the damping coefficient kd, we have the amount of difference in velocities, vq minus vp, divided by the rest length, times the dotted producted with how much that's actually in the direction of the spring. And then we have the direction that the force would need to act on as the final term. So this is relative velocity here. This is the spring direction. And putting it all together, we get this big, complicated formula that's actually, even though it's big and complicated, it's easy to write code that actually uses this force. And so here's the actual code. So I left out the header stuff, but you can see that we've expanded our code. We still are initializing all the particle forces to 0. And then for computing forces, we have, instead of just calling some ambiguous compute forces, we can say that we compute the direction between the two positions, we take the norm of that direction, we compute the relative velocity, we have our formula for the force, we add that force to one particle and subtract it from the other, and then our time integration is exactly the same code as before. And I would do a live demo, but we'd have to switch out laptops, so I'll save that for the very end. And I'll turn it over to Tamar to talk about mathematical models.
Thanks, Adam. All right, so we're going to talk about some of the mathematical models that are underlying physics-based animation. And among the most important here are Newton's laws of motion. So Newton published these in the Principia in 1687, and that includes 3 laws of motion. Newton's first law, the law of inertia, Newton's second law, F equals ma, and Newton's third law, which is the law of action-reaction. And among other problems, Newton studied the motion of planetary bodies. And these laws can be applied to a body as a whole, or we can also think about applying them to a particle which carries a mass or a point mass. So Newton's first law says, a body persists at rest or in uniform motion in a straight line unless acted upon by a force. This is also called the law of inertia. And for hundreds of years before, actually a little bit before Newton's time, because Newton wasn't the first one to formulate this, but for many hundreds of years, people just assumed that they took the Aristotelian view, which assumed that bodies had a tendency to come to rest unless acted upon by a force. So that's very different from what this law is saying. And it seems like a natural assumption. If we observe things in our world, we see that if we roll a ball across the floor, it eventually comes to a stop if we do nothing else. So from knowing now Newton's law, we understand, now we know that is due to forces actually acting on the ball to stop it. In particular, friction is actually decelerating the ball. But for many hundreds of years, it was just thought that was the tendency of objects. Okay, Newton's second law, also just called F equals ma. So this says that the rate of change of momentum of a body is directly proportional to the force applied to the body. So here's our momentum for the body, p, it's a function of time. And momentum is equal to mass times velocity of the body. And now this law is talking about the rate of change of this quantity. So we have our time derivative here, ddt of the momentum. If the mass is constant, we can move this derivative inside, and now we have the time rate of change of velocity, and we write that as acceleration. So that's our ma. And then Newton's law tells us that's equal to the net force acting on the body. So if we have this particle carrying with a mass m, and it has 2 forces acting on it, that F1 and F2, then the F in Newton's law is the sum of those 2 forces. And in this case, the horizontal components cancel out, and so we just have double the vertical components, that's F. Another thing about Newton's second law to appreciate is that if we divide both sides by the mass, then this is telling us that the acceleration is inversely proportional to the mass. So if you have a large mass and you apply some force, you'll get a small acceleration, whereas if you have a smaller mass and you apply the same force, you get a larger acceleration. So we know this from a practical experience where if we apply a force to a pebble and throw it, it's going to accelerate quite a bit, it's going to travel pretty far. If we apply the same force to a boulder, we don't really expect too much to happen. So that's this inverse relationship between acceleration and mass. And importantly, Newton's second law is really the basis of many, many methods in physics-based animation, because what it is an evolution equation. So it tells us how to evolve things in time. We have some initial conditions, and then we have Newton's law, which is a rule for how things are going to change in time given initial conditions. So most problems are too complicated to just solve on paper, but we can discretize things and solve them numerically and evolve them forward in time. In applying Newton's law, there's kind of, the way you approach it is kind of like you would this Freebody diagram where you have a picture of all the things in your system, and you have to characterize all the forces acting on something so that you can arrive at the net force acting on something to integrate forward in time. And as Adam already mentioned, Newton's second law is really a second-order ODE. Now, a second-order ODE can be converted into a first-order system of ODEs, and given some initial conditions, then we write down all the different forces, and we use this to evolve forward in time. And we do the same thing if we have many different particles. So for each particle, we're going to characterize all the forces acting on that particle and apply initial conditions, and give initial conditions, and then apply F equals ma to evolve in time. Newton's third law. Now this tells us that For every action, there is an equal and opposite reaction. So restated, if body 1 applies force F to body 2, then body 2 applies force minus F to body 1. So let's look at some examples of this. So here's two particles connected by a spring. And there's going to be a spring force associated with the spring that Adam talked about. And the spring force will then be applied to one particle. If the spring force is F, that will be applied to one particle, and by Newton's third law, minus F is going to be applied to the other particle. Another example is in the collision of two particles. So if two particles are moving toward each other and they collide, there'll be a force generated, a pair of forces that will prevent them from interpenetrating, and we'll have F on one particle, minus F on the other particle. And also, if we look at this particle just resting on a table or on a surface, let's say, so the particle is feeling, if it's stationary, it's just feeling minus mg, the force of gravity, and something, since it's stationary, something has to cancel that so that there's no acceleration. So it's going to feel an equal force in magnitude, opposite in direction force from the table pushing back on it. And that's going to be a force minus mg pointing up, which will directly cancel the gravitational force. So we get a zero acceleration. Okay, and Newtonian mechanics are one formulation of classical mechanics that's very commonly used. And as we've seen, it's based on vectors in Cartesian space. So I drew a picture here of a pendulum, a problem of a swinging pendulum. And if we're solving this using Newtonian mechanics, we might have two coordinates, x and y, describing the mass at the end of the pendulum. And then we have to formulate all the forces, including the constraint force that holds this, that represents the tension from the string, or the connection. There's another set of approaches called analytical mechanics, and those are based on constructing an integral quantity called an action, and then applying variational principles to that action. And those are a different and powerful set of approaches that are also used in physics-based animation. Unlike Newtonian mechanics, they let you use a more general set of coordinates, and they can actually describe the problem in terms of coordinates that already respect any constraints. So for example, using analytical mechanics, we could solve this pendulum problem just by looking at the angle theta. Okay, so in addition to Newton's laws and analytical mechanics, other physical principles that are very important in physics-based animation are called conservation laws. So a conserved quantity is a quantity that cannot be created or destroyed. So many of the quantities that we're interested in that are conserved include mass, linear momentum, angular momentum, and energy. And conservation laws, we can use them to derive other evolution equations. They're also important in that they can inform the choice of discrete approximation to continuous equations. So what we're doing right now is we're writing down a bunch of continuous equations like Newton's second law and the conservation laws we'll see. But then when we go to actually simulate those, we're going to have to discretize them, and that's a whole field of study. And there are many different types of choices you can make in constructing a discrete method to approximate continuous equations. Taking into account conservation laws can be an important thing to do when constructing these discrete methods. So that consideration has implications for visual quality, numerical accuracy, and also what's called numerical stability. Okay, so first let's talk about conservation of mass. So mass cannot be created or destroyed. This is called the inexact conservation law, but that's sort of beyond the scope of our course because that relates more to mass energy equivalence and things. But for our purposes, mass is conserved, and we'll look at some particle-based methods and also grid-based methods. So here, just as an example, in a particle-based method, mass is going to be very naturally conserved. Particles are going to carry the mass around with them, and so as long as we are tracking particles and doing correct bookkeeping on them, we won't lose mass. Grid-based methods sometimes have more trouble with this. Okay, another important quantity that's conserved is momentum. So we can also relate these conservation laws to Newton's laws. So by Newton's second law, if there's no net force on a body, then by Newton's second law, we can see that the time rate of change of momentum is 0. So the momentum is a constant. And very similarly, if there's no net torque on a body, the angular momentum of it will be conserved. We can also relate this to Newton's third law because forces are occurring in pairs that are equal in magnitude and opposite in direction. So if we're looking at the total momentum of a system, when the forces arise in pairs, those pairs will cancel each other, and the total momentum of a system will be unchanged. So many internal forces in an object have this property, like internal elastic forces and pressure and so on that we'll talk about. And this also applies to angular momentum. So if we measure the change in angular momentum associated with a pair of forces of equal magnitude and opposite direction, we'll also see that they don't change angular momentum. Okay, so if we have a bunch of particles interacting with each other, then looking at the system as a whole, these forces will occur in pairs, and our momentum will be conserved. So conservation of energy is another principle. You might encounter it in physics class or something like this, where because of conservation of energy, we can study a problem like this. We have an object initially at a height h0. So initially, if it's at rest, all of its energy is in the form of gravitational potential energy. And it specifically can be approximated by mgh0. And then we can, as the object is falling because of conservation of energy, if we ignore air resistance, so because of conservation of energy, it's going to have to satisfy this equation, which says that as it's falling, some of its gravitational potential energy is going to get converted into kinetic energy. But altogether, the sum of kinetic energy and potential energy has to stay that constant that we initially had. And then we can do things like solve, for example, for the speed of the object when it hits the ground by plugging in h of t equals 0 into the previous equation, the middle equation there, and solving for the velocity. So those are principles that apply to our quantities mathematically, and numerically. When we discretize our equations, we don't always exactly carry over those principles, but we can also devise schemes that do have numerical conservation. And there are uses for both types of schemes, so it's not that there's one way that you have to do it. But it is an important thing to consider. And what we see is that in many schemes, sometimes momentum or energy or both may grow or decay non-physically. Sometimes this is really obvious, like we'll say that if we have an instability in our simulation, that means that the energy is actually going to infinity in some very small amount of time. And we will say that our simulation blew up. It's pretty dramatic, and I'll show you, it does actually look quite dramatic, so you can't really miss that case. Other times instabilities can arise, but be kind of controlled, and then they just look like kind of non-physical oscillations. So another common problem is that the motion is very damped. So these are sort of opposite ends of a spectrum. And sometimes to get your simulation to be stable, you add damping, and then damping can be sometimes too much, and you can notice that it looks damped. So here's an example. This is a simulation that blows up, and I don't think I need to explain that, so you can see it. Okay. So if you start writing simulation code, you will see this. At least it makes itself very obvious, so that's nice. Right? And here's a simulation where both momentum and energy are lost. And so even though this cube is just spinning, so physically it should just continue to spin because of conservation of angular momentum. But what happened is its motion was damped, so it actually slowed down to a stop. Another place that we use conservation laws is in deriving evolution equations for continua. So there's a branch of mechanics called continuum mechanics, and we especially study it for simulating soft objects and simulating fluids. So in the continuum mechanics, we say, well, we're interested in this phenomenon on a scale that's large enough that we can treat it as a continuous material rather than something that's made up of a bunch of molecules or particles. And so we have the view over on the right, which is that this is a continuous material. Now, if you work on this stuff, you'll run into these things. So it's very common to define this, what's called a control volume, which is we draw some arbitrary region here, or if it was a three-dimensional thing, we draw an arbitrary volume, and we talk about the material in this volume. So we have the volume is omega, and the boundary is d omega. So for example, let's look at conservation of mass, and we'll derive a evolution equation for density by just using conservation principles. Okay. So mass is conserved. So we drew this arbitrary volume omega, and rho here is a mass density. So if I integrate the mass density over the volume omega, I should get mass. And because it's conserved, I'm going to talk about the time rate of change of that. Because it's conserved, it can't be created or destroyed inside of omega. So there's only one way that it can change in time, which is flow through the boundary. So on the right, this is a surface integral. It's an integral over the boundary, and it's representing the flow of mass density into the volume or out of it. So I drew a picture here with V and N. You can see that in that integral, the dot product appears. And in this picture right now, that dot product will be positive. But there's a negative sign, which means that we're going to lose mass. And that makes sense, because the velocity is pointing out of the region, so stuff's going to flow out. On the other hand, if velocity is pointing in, stuff is going to flow into our region. V dot n will be negative, and then the minus sign in front of that integral will cancel that, and so it'll be positive. So if stuff flows in, we're gaining mass from the outside. And if we have flow tangential to the boundary, that's zero, nothing's happening, nothing's flowing in or out at that point. So we integrate all around the boundary and add up all the stuff that's flowing in or out, and that tells us how much our mass is changing inside the volume. So at this point, we're done with the physics, and now it's all just math. So the math says, okay, well, you apply a theorem called the divergence theorem. We convert a surface integral to a volume integral. We move everything to the same size. We move some differentiation under the integral, and we arrive at this equation. Okay, so to get from the first equation to the second is some important calculus laws, and ones that if you work on this stuff enough, you'll want to be familiar with because they come up. But anyway, now we have a continuity equation that is not under the integral sign anymore. So we also had to make some assumptions about smoothness and things like that. And this continuity equation, when you see an equation of this form, here's the form of it. It's a local conservation law, so now it applies pointwise. And it says that the rate of change in time of some value u, which is conserved, is equal to the divergence of a flux function. So if you see something like this, you can directly relate it back to that integral equation we had, which is the term that has a time derivative is coming from rate of change of that quantity in a volume, and then the term with the divergence is coming from flow in or out of the boundary. But it's been converted into a pointwise equation now. Okay. All right, so now we're going to talk to you about a few different types of materials, particularly rigid bodies, soft bodies, and fluids. So before we get into a rigid body, let's count degrees of freedom. So let's look at this system. We have 4 different particles. Each particle has a position. And if we're in 3-dimensional space, each position has 3 numbers, so x, y, and z. So if we count degrees of freedom here, which is the number of parameters that we need to represent the configuration of the system, if we count the degrees of freedom, we get 12. Okay. Now, if I have an object where I really don't care about how it deforms, how it squishes, or I just want it to maintain its shape, and I just want to be able to simulate how it translates and rotates in space, a common approach is to say this is going to be represented as a rigid body. So physically, nothing is completely rigid, because if we apply enough force, we'll cause it to deform and break also, but also to deform. But visually, many times we're not interested in deformation. We're just interested in something and its rigid motion. So when the deformation is negligible, we can use a rigid body approximation. And in the rigid body approximation, instead of thinking of our object as being made up of a bunch of particles that are connected by some very stiff forces, we're going to just say that actually there's a constraint between all these particles. So on the left, I might just put a bunch of springs between my particles and say, well, these springs are very, very stiff, so there's not going to be much deformation. And that's fine, you can do that in your mass spring system, but what you'll find is that you'll be forced to take very small time steps, because those stiff springs make information travel very quickly through your system, and if information is traveling through your system very quickly, like if I push on the podium over here, if I push hard enough, the whole podium is going to move. And what that means is that I pushed over here and information traveled over here right away, pretty much. Whereas if this was really squishy and I pushed over here, then there would be some local deformation around this area, but it might take a long time to get here, or it might be completely damped out before it gets here. So if you have very stiff springs, information travels very fast, and you typically will either need very small time steps in your simulation to capture that traveling information, or what's called an implicit method, which is kind of very closely related to small time steps. So instead, we're going to switch to constraints, and in this case, we go even a step further, which is we say, well, actually, in this idealization, we don't need the 12 degrees of freedom to represent this object. We actually only need 6. And even if we had many more particles on this, sampling this rigid body, we still only need 6 degrees of freedom. So for a rigid body, the 6 degrees of freedom, this is in 3-dimensional space. Our 6 degrees of freedom are 3 degrees of freedom in position and 3 degrees of freedom in orientation. So this makes sense if I think of this object as rigid. I have 3 numbers that describe where I'm placing it. And that's the three numbers in x. And now I have 3 more numbers that will describe how it's oriented. So imagine there's a surface of a sphere, and I'm pointing the top of my bottle to some point on the surface of a sphere. So that's 2 more numbers, because a sphere has latitude and longitude. And now I have a third left over, and this bottle wasn't the best example because it's rotationally symmetric, but the third one is rotating about its own axis. So if this bottle was not symmetric like that, then you would see that better. But that's my third one. So I have 6. In 2D, we only have 3. Okay. So a little more about rigid bodies. It's helpful to talk about the center of mass of a rigid body. And here's a formula for center of mass. If we think of the body as made up of a bunch of particles, then we are taking an average of the position of the particles. But it's not just a regular average, it's a mass-weighted average. So if one of these particles is more massive, then the center of mass will tend toward that position. But if all the particles have the same mass, then I can cancel that mass out, and I would just have all the positions divided by 4 in this example. So the center of mass formula is right there, and here it is more generally. If I have a bunch of particles, I just take a mass-weighted average of all the positions representing that body. Okay, so when we're doing rigid body simulation, we need to think about points on the body other than the center of mass. And in order to describe points on the body, we can label them by fixing a coordinate system to the body, and we call that object space. So that's shown on the left. So object space, it's very convenient to put the origin of object space at the center of mass, and that's what's typically done. And then every point on the body can just be described by a vector r0, which points from the origin to that point. And to distinguish from object space, we relabel the regular space that we normally talk about as world space. So that's just regular space where things are moving around and so on. Now, a rigid body has a linear velocity, and this one behaves very much as if all the mass of the rigid body was just concentrated at its center of mass. So this is its linear velocity, and that's the way that my object is just traveling through space. So it's just doing this, there's no rotation. For example, in this object, then that's the linear velocity. And then we also have an angular velocity, and that represents the rotation of the object about its own center of mass. So it can be translating through space and rotating at the same time. And I can capture both of those as linear velocity and angular velocity. Now, if I want to know the position or velocity of some point on the surface of the rigid body or in the interior, I can express it from the center of mass and orientation of the body for the position. So the position of a particle on the rigid body, I can find it by applying the orientation or rotation r of the body to the vector r0, and then adding the current translation. So that way I can find where any given point on the body is at any given time. And to find the velocity of a point on the body, you can differentiate the above equation. You get this formula v plus omega cross r, which you've probably seen before, so that for velocity of a point on a body. So for example, let's say you're on the merry-go-round, and you're at the center of the merry-go-round. So there r would be 0. The merry-go-round is spinning, and so there at the center of the merry-go-round, the velocity is just v. So usually for merry-go-rounds, that's 0, but it could be something else. And then because of r, you can see the particle velocity here is, because of the r there, as you move out towards the edge of that merry-go-round, you're going to feel like you're going to be traveling faster instantaneously. So, okay. We also talk about the linear and angular momentum of a body. If I want to, I can find an expression for the linear momentum by summing over all the particles on the body. And so I sum up the linear momentum of every particle on the body, sum of mivi, and that's my total momentum. And then by putting my origin at the center of mass, that simplifies into the total mass of the body times its linear velocity. Now we can do a similar thing for angular momentum. And after some manipulations, which you can find in our course notes, we get this expression on the bottom for angular momentum. So the angular momentum L is equal to this inertia tensor I times omega. So if you compare this to the equation or expression for linear momentum, there's an analogy here. The angular momentum is similarly something like mass times a angular velocity. And this inertia tensor is this, not just the mass like m, but it also represents how mass is distributed throughout the object. This is kind of what the inertia tensor looks like. So it depends on time, but we can also calculate it in the object space. That's I0 at the bottom. So we can calculate it in object space once at the beginning of our simulation, and then based on how the object is rotating in time, we update the inertia tensor based on the current configuration. So inertia tensors, there's an example we're all familiar with, which is an ice skater rotating on the ice. So as the ice skater is rotating on the ice, she can pull her arms in. Now first of all, she has conservation of angular momentum. So if we ignore the friction with the ice, which is relatively low, but it's still there, but she has conservation of angular momentum. And as she's, so this quantity L is going to be, let's pretend that it's fixed. As she pulls her arms in, what's going to happen? If we look at this expression for I, we see that it sort of depends on these r squared terms in it. So it has these r times r terms in it. So it's like r squared, where r is like the extent of the body. And so as she pulls her arms in, those r's will get smaller because she's pulling her arms in. And so the inertia tensor is getting smaller in some sense. So if angular momentum is conserved and the inertia tensor is getting smaller, then omega will have to get commensurately larger. So we're all familiar with that phenomena where the ice skater pulls her arms in and they're rotating faster and faster. Angular momentum is being conserved, but angular velocity is increasing because the extent of the body is decreasing. So for a rigid body, the linear momentum behaves very much as if it was a particle. So if there's no net force, both linear momentum and velocity are constant. But if angular momentum is a little bit of a different beast. So if there's no net torque, angular momentum is constant, but the angular velocity is not necessarily constant, just as in that example with the ice skater. So we have something like Newton's second law for rigid bodies, and now it includes another term. So instead of just F equals ma, we also need a term for torque and angular momentum. And these are called the Newton-Euler equations. And so our whole evolution of our rigid body system can be summarized in the four vector equations at the bottom. So the time rate of change of position is velocity, time rate of change of the orientation, and the time rate of change of linear and angular momentum are the force and torque, respectively. So here's our little structure for a rigid body, which Adam will go over later as well, but thought I would bring this up here now. So we could track the mass of the rigid body. There's I0, which is the inertia tensor in object space. We have the current position of the body, the linear momentum, a force accumulator, a matrix R, which represents the current orientation, L, which is the current angular momentum, and then torque to accumulate all the torques, so we can apply the Newton-Euler equations. Okay, and with that, I'll pass that to Adam.
Good to be back. So now we'll talk about adding elasticity and damping. So this is going back to F equals ma. And when we do this, we add some elastic and damping forces. You can imagine rewriting this in terms of displacements. So instead of having x minus u, you just have the displacement d, and the velocity is equivalent to the change in displacements. But when we look at the left-hand side, we've sort of written this, though, as ma equals f. So here we have the old f equals ma that we're used to. This term is the damping term. There's some damping function of velocities that provides a force on our body. This is things like friction, internal friction, forces like that. And then here's our elastic forces. These depend on displacements, how far the world pose is from the rest pose u. So world is going to be x, and object space will be u here. This is sort of a generalization of spring stiffness. It's called the stiffness matrix. It's sparse, it's symmetric, it's diagonally dominant, which means that the values on the diagonal are no smaller than the values in the rows and columns, the sum of the rows and columns. And its rows and columns all sum to 1. This is 0, sorry. It is positive semi-definite, so for any vector, v transpose kv will be 0 or some positive amount. It's the negative Jacobian of forces, and what that, and I think here's the formula. It's the negative Jacobian of forces, which means that it's the negative partial derivative of f with respect to the degrees of freedom x, and then it's also the negative Hessian of energy. So if our energy eta there in that final term, the partial derivative of energy with respect to both xi and xj, the two particles that are interacting. So how do we calculate elastic forces? We come up with some deformation function, which is a function of the world pose and the rest position. We compute the deformation gradient from this deformation function. We then compute the strain, which is a function of the deformation gradient. Remember, the strain is this dimensionless quantity that describes how the shape has changed. We come up with the stress, which is a function of strain, and this is where the magic comes in for material modeling. So different materials have different stress-strain relationships, and materials like skin and other biological tissues have really interesting and complex stress-strain relationships. And then we compute some energy, which will be a function of the stress and the strain. And then we compute forces, which are the negative gradient of that energy function. They try to minimize the energy. So let's look at the deformation and its gradient. So we have this object on the left that's going to be in object or rest space. And then there's some deformation function x of u, which takes some position u and maps it to some position in the world space x. And so there's 3 points here in the left object and the mapping of those 3 points in the right. And so we can write x of u, this function, this deformation function, as x of u0 plus f of f times u minus u0, where f is a linear function. It's typically a linear function. If we take the gradient of this deformation function, we get the partial derivative of x with respect to u, and this is just f. And so we call f the deformation gradient. The strain is a measure of deformation. It's dimensionless, it has no units, and it's a function of the deformation gradient. There's 3 common strains used in computer graphics. There's Green's finite strain, which is quadratic. You can see that because we're taking f and we're multiplying it by itself. It works well because it's invariant to rotations. It's the first one that was really used extensively in computer graphics. There's Cauchy infinitesimal strain, which is linear in F. We're just adding F together. We're not multiplying it by itself. Unfortunately, this strain metric suffers from large artifacts under large rotations. And then there's the much newer, not so new now, but it's much newer than the other two, the co-rotated strain model. And this is the one that's most commonly adopted in computer graphics. Here what we do is we first compute a polar decomposition of F to remove rotations, to explicitly remove rotations from the measure. And then we take the, basically the Cauchy's infinitesimal strain of that. So we get something that's linear once we've undone the rotations. The rotations are still nonlinear, but once we've taken them out, we get a linear strain metric. Stress is then a function of strain. Stress has units. It's newtons per meter squared. And models of stress-strain relationships can be highly complex, especially with organic materials. This is really where the magic of material modeling goes in. If you were doing a PhD in material science, you would be coming up with stress-strain models. In general, for a linear stress-strain model, we have the stress is equal to some linear function of the strain. C is mapping 9 degrees of freedom to 9 degrees of freedom, so it has 27 possible degrees of freedom. But once we consider that most materials are isotropic, and we know that stress and strain are both symmetric, we actually get down to 2 material parameters for an isotropic material. Lambda and mu is one way to characterize that. You can talk about the Poisson ratio and these are the Lemay constants, but you might have heard of the Poisson's ratio and different elastic modulus. But you get something that looks like this, where lambda is multiplying the trace of epsilon, which is just the sum of the diagonal, multiplied by the identity, and then we have 2 mu times epsilon, which is just the measure of the strain, some constant times the strain. I'll go back and say one more thing, if I can. The first term there, the lambda term, is actually trying to penalize changes in volume. So the trace of epsilon is, to a first approximation, how much the volume has changed, whereas the second term is penalizing all deformation. The elastic potential, so this is the energy in our system, is 1/2 of the stress times the strain, where that symbol is tensor contraction. You're basically multiplying each of the individual components of your stress and strain together. From that, we can compute attraction, which is the stress times some direction. And then we can also compute forces, which are just going to be the partial derivative of our energy with respect to our degrees of freedom. And if you think about it, all of physics is basically doing gradient descent. You have some energy function that you'd like to minimize. You find the direction that minimizes that the fastest with respect to whatever degrees of freedom you have, and you go in that direction, and that's what forces are. You can also characterize forces as being the integral over the boundary. Using the divergence theorem that Tamar was talking about earlier, you can characterize them as the integral over a boundary of the stress times the normal at that point of the boundary. And then plasticity is sort of an advanced topic, but the idea behind it is that we take this deformation gradient and we break it up into 2 parts, an elastic part where we're going to have forces that try to undo it, and then a plastic part which is just going to be permanent. And then I'll let Tamar talk about fluids.
Thank you, Adam. All right. So fluids, we have a lot of different kinds of fluids that we encounter in our day-to-day lives even. I put up some different pictures here of some different types of fluids. So we have some very viscous honey on a spoon. We have a big ocean with small waves. We have an ocean with crashing, breaking waves. And then we have this picture of a lime with some bubbles of gas forming inside this liquid. And this curling smoke, and also this large-scale atmospheric flows. So defined intuitively, a fluid is something that takes the shape of its container. And mathematically, a fluid is a material that can't support a shear stress. So meaning that if I push on the fluid with this force tau, or the stress tau that's shown in the drawing, the fluid will not be able to maintain that shape and push back. If you think about some kind of like elastic ball or something, if I do that to a ball, I can hold my finger there and the ball will just stay like that, I let go, it comes back. But the fluid doesn't behave that way. If I push on it that way, it's going to start flowing. So fluids don't support shear stress, that's those sideways ones, but they do support normal stress. So I can squeeze something, I can fill a balloon with air, and the balloon is trying to squeeze that air, but the fluid is fighting back, so it's pushing back, and it's causing the balloon to maintain that shape. So fluids do support normal, that's a normal stress that's orthogonal or perpendicular to the boundary. The fluid equations that we're typically using are in a particular regime, and in the regime of intermediate Reynolds numbers, it's called, our incompressible fluids look like this. These are called the Navier-Stokes equations. And it's much more complicated than F equals ma, but it's actually a form of F equals ma. It's just, so one difference is that these equations have been divided by volume. So rather than having units of force, they have units of force density. So instead of a mass, we have a mass density. And then on the right-hand side, that all those forces are a force density, actually. So that should say force density, really. Now, so the rho there is representing our mass. The quantity in parentheses is analogous to acceleration, or it actually is acceleration, that is. And on the right-hand side are all the different forces that are acting in a fluid. And then we have this other equation, which is our incompressibility, which I'll mention. So here's density, our velocity. So the fluid moves at a certain velocity, and these are all the terms that depend on that. Pressure gradient, viscosity, and any other forces like gravity, perhaps sometimes surface tension can be put in here, or maybe interaction forces with other things. Okay, so the first thing that looks different about the fluid equations as compared with F equals ma is the way that A looks. So the explanation for that is that a lot of times when we're simulating fluids, not always, we're taking this different point of view, which is that we want to track a velocity field. Rather than tracking particles and following the velocities of particles, we're going to place points down in space, and we are going to measure the fluid velocity at those points at any given time. So here, for example, at the red dots, I'm measuring velocity, and that's u of x, my velocity field. But Newton's law tells us about the acceleration of particles, not the acceleration that's going on at a point when you're fixed. So if I want to apply Newton's law and get my Navier-Stokes equations, I need to think about the acceleration of a fluid particle moving through this field. So I'm going to write down my acceleration of my particle as a time rate of change of the velocity. And now this is where I relate my velocity of my particle to the velocity of my fluid velocity field. So the velocity of a particle will be the velocity u at the point where the particle is located. So at that point, those two things have the same velocity. So I just plug the u in there. And now the rest is math. So to differentiate u, we have to differentiate with respect to the second component, so that's du dt. And then with respect to the first component, we apply the chain rule, du dx, and then dx dt. And that x is just that velocity again, and so we get this expression. So really, this kind of complicated looking derivative is just the acceleration of a particle moving through the flow at that point. This is called the material derivative, or the substantial derivative. It has a lot of different names. Material derivative is one of the most common ones. Also particle derivative. Okay, so that explains that term. And then pressure forces show up in our fluid in this minus the gradient. So we're talking about a specific fluid that's incompressible, and we'll talk more about that. But in this particular case, it's really the role of the pressure to resist any attempt to change the volume of the fluid. So if I take that balloon and I'm trying to squeeze down, but the air inside is going to resist that. It doesn't want to change volume. And it's going to do that through pressure forces. Now this pressure, if you look at this pressure force, another thing we can see in it is that it's the negative gradient. So you know gradient of a function points from small values to higher values. So the negative gradient points from higher values to smaller values. So if I have like a tube of fluid and I'm squeezing here, there's going to be a higher pressure, and it's going to force the fluid down to the other side of the tube from higher pressure to lower pressure. This term, which is mu, we would read this as mu Laplace u. So this term describes viscous forces in the fluid. There's a drawing here of a kind of classic experimental setup, which is that we have a plate on the bottom, which is stationary, and then we have another plate on top, which is moving to the right with some velocity. And the black arrows here show you the velocity profile that the fluid will take on from the top plate to the bottom. So the fluid is going to it's going to stay stationary next to the bottom plate. It's going to move with the top plate moving, and everywhere in between, it's going to have this profile as it goes from moving with the top plate and moving to the bottom plate. So the way that it does this is through these viscous forces. So viscous forces describe the tendency of layers of fluid to move to try to cause neighboring layers to move at the same speed, or to try to move at the same speed as neighboring layers. And different fluids have different values for this coefficient mu. So for example, honey, well, its viscosity actually depends very strongly on temperature. If you've ever tried to pour some honey and found you had to put it in the microwave to get it to flow out of the bottle. But it's about, in this example, 5 orders of magnitude larger than air. And then water is defined to be 1. And the operator that's measuring kind of how much the velocity is different from its neighbors at a certain point is this Laplacian, this differential operator that we'll talk about more later. So we can think of the viscosity as this internal friction in the fluid. Another thing that makes fluid simulation kind of challenging is getting boundary conditions right. So you'll find often boundary conditions are some of the trickier parts of simulation, along with collisions and things like that. For a fluid, a very common boundary condition, especially a viscous fluid specifically, is the no-slip boundary condition. So the fluid wants to stick to the walls, wherever it's touching walls. Another kind of classic experiment is shown at the bottom, which is flow through a pipe. So at the walls of the pipe, the fluid is stationary, so the pipe is stationary, so the fluid will want to stick to it and be stationary at the walls. And then it takes on this parabolic profile with a maximum right in the middle of the pipe where things are flowing most freely. But also we have like this ball in a container of water. Along the edges of the ball, we might also have a no-slip boundary condition. So this boundary condition, this sort of standard one, but there's also a lot of research about this, how to get these get boundary conditions right in different scenarios. It's not always necessarily the one we want to use if we can't resolve the boundary layers, for example. And then F is capturing external forces. We put gravity there. There are models that put surface tension there. We can also put interaction forces or control forces. So in graphics, we sometimes want to make the fluid do things that are non-physical. One possible way is to try to drive the fluid into some sort of configuration by putting forces into F that are targeted toward whatever we want to drive it into. And there are other methods for that too. Now, the second equation. Now the first equation is F equals ma, so it's related, it's coming from conservation of momentum. It's actually our momentum equation. And the second equation is actually coming from conservation of mass. So we saw from the, we derived this conservation of mass equation. If you assume the density is constant, as it is in an incompressible flow, then you can, that time derivative goes away and you can pull rho out of the spatial derivative and you're just left with this incompressibility condition. If we look at this a little more closely, what this incompressibility condition is in any region, the fluid will not compress or expand. And we can also convert this to a boundary condition, a condition on a volume at the surface of something. So if I look at some region of fluid, the net flow through the boundary has to be equal to the net flow out through the boundary. Otherwise, if I have more stuff flowing in than coming out, that means that the fluid will have to compress in order to accommodate that stuff. Or if more stuff is flowing out, then the fluid will have to expand to fill that area, but it can't do that because it's incompressible. Okay. All right, so with that, I'll switch back to Adam.
Okay, so one of the things that's actually often overlooked when you first start studying physics-based, can you hear me? Is it good? Okay. One of the things that's often overlooked when you first start studying physics-based animation is this sort of fundamental thing. And the reason it's overlooked is that it's so fundamental to how we discretize things that we often don't call it out. So I think it's important to actually make this point. So there's two fundamental ways that we can look at spatial discretizations. They're the Lagrangian viewpoint and the Eulerian viewpoint. And this boils down to an Eulerian reference frame is fixed. The reference frame, the place where you're making measurements, stays put. And in a Lagrangian reference frame, the frame moves with the material. And so the example I like to use is that if we had this river flowing down the river, and we wanted to measure how fast it was flowing, one thing we could do is wade out into the water and measure how quickly the water moved past us, right? And that corresponds to an Eulerian framework because the little happy guy is just staying put, right? The samples are not moving. Another way that we could do it is we could get out inner tubes and we could see how fast we move down the river, right? And that corresponds to the Lagrangian viewpoint because we're measuring how fast we're going and we're moving with the material. When we're adopting one of these viewpoints, we will typically write either the material derivative that Tamar was talking about earlier, or we'll write just the basic derivative, the simple derivative dy dt. There's three common discretizations in computer graphics. There's grids, meshes, and particles. Regular grids are a set of hexahedra, just a regular grid. Everything's the same. You have some dimensions in x, some dimensions in y, some dimensions in z, and there's some grid spacing h that tells you how far apart your samples are. One of the big advantages is that they're simple. You have fast operations. Point location is trivial, right? It's a divide and maybe a couple of subtractions. It can take advantage, and one of the big advantages is it can really take advantage of the structure to get lots of efficiency. So grid-based methods tend to be very, very fast. One of the disadvantages is that it's hard to track things over time. So as something moves through the grid, you end up resampling it a whole bunch, and you can end up sort of averaging and smoothing whatever your signal is. It's also difficult to handle non-grid aligned boundaries. So if you have some regular grid and you have something passing right through the center diagonally, it's hard to handle that sort of boundary condition. A really common structure in computer graphics is what we call the staggered grid. Here we're showing how you would store different variables on the staggered grid. So we're storing pressures, for all pressures in the center. So this is the P, I, J, and K in yellow. For the velocity that's flowing in the x direction, we'll actually store that uijk on the x faces of our grid, and we'll store fluid flowing in the y direction in the vijk on the y faces, and then we'll store w on the z faces. So we're storing, I guess here it's 7 scalar quantities to track both the velocity and the pressure. This is in contrast to a co-located grid where we would store everything in one single place. The staggered grid tends to offer us second-order accuracy and much better simulations for negligible extra cost. There is some extra cost that's incurred, but we get much better accuracy for negligible extra cost. It's almost always worth it. Meshes that we adopt in computer graphics are typically simplicial complexes. And simplicial complexes are either triangles in 2D or tetrahedra in 3D, and you can have higher order simplicial complexes, but I don't run many simulations in 4 dimensions. The advantages of simplicial complexes is that it's really easy to map to previous points in time. This allows us to compute deformation gradients and things very easily. It's really also, well, it's not really easy, but it's possible to conform your elements to boundaries. A disadvantage is that it's really difficult to generate these meshes. There's some recent work just in the last year or two at SIGGRAPH that's sort of robustly generating tetrahedral meshes, but this is recent work, right? This is the last year or two. 5 years ago, this was really sort of an open problem, and it's still pretty difficult. And it's difficult to perform some operations, such as point location. Often, if you want to do point location in a tetrahedral mesh, you build some auxiliary spatial map that allows you to do that quickly in something like log n time. Otherwise, you have to search every single element and say, is this point in your element? And then there's particles. Particles may be the most common thing used in the visual effects industry in particular, and they're simple. It's easy to map to previous points in time. The difficulty with them is that it can be hard to perform integration because particles don't really partition space. There's no way to draw a bunch of circles and have that partition space. There's always either overlap or there's gaps. What's really common in computer graphics, especially in the last decade or so, is to adopt some sort of hybrid structure. Here you hope to get the advantages of the underlying structure, and as an example of hybrid structure, it would be particles flowing through a grid like in the NPM method. And you get the advantages of the underlying structure, you get the advantages of the particles tracking things through time, and you get the advantages of the structure of the grid. The disadvantage is that they tend to end up being more complex methods, and then there's computational costs and accuracy costs when you map between the two structures. So every time you have to map from the grid to the particles or the particles to the grid, you lose something. And Tamar does interpolation.
Thank you, Adam. All right, so if we're storing values for some function on some points on the grid, many times we might want to have a value from a different point other than where they're stored. So at that point, we will need to interpolate the values to the point that we're interested in from the ones that we have stored. So here's an example. In our fluid simulation, the term that looks like the funny acceleration, that's called advection, and one common way to discretize that in fluid simulations is to say, okay, I need to update the velocity that's labeled here u for the next time step. Well, how do we do that? Well, we say, okay, let's say that we have a time step of size dt, so we're going to trace back, based on that velocity times the time step dt, we're going to trace back how far we're going to travel over that time step going backwards. And we're going to say, okay, over this time step, stuff is going to flow from that blue point to the point I started at. And so my new velocity at the point that I started at should be whatever the velocity was carried by the particle, whatever the velocity was being carried by the particle back there. So now I have this interpolation problem. I want to interpolate from all the neighboring particles to the point where I want to sample. Okay, and then I use that, and that's my new velocity. So we'll just briefly go over some interpolation. Here's a simple one-dimensional interpolation. So over on the left, I'll call that 0, and my parameter t will be 1 over on the right at f2. So when t equals 0, I want to have my value be f1, and when t equals 1, I want to have the value of my function be f2, and everywhere else in between, I want what's called linear interpolation. And so here's the formula at the bottom for this simple case. So you see this is a weighted average of the value at f1 and the value at f2. Now, what are the weights? Well, t is something that's between 0 and 1. And so the weight on f2 is just going to be t. Now, the weight on f1 is 1 minus t. That's also something between 0 and 1. And specifically, the weight of each point is going to be the length opposite that point. So if you look at f1, the length of the segment opposite f1 is 1 minus t, and that's its weight. If you look at f2, the length of the segment opposite f2 is t, so that's f2's weight. So I don't know if this works. Okay. So here, the weight of f1 is this length, and the weight of f2 is actually this length. So that's captured in that formula right there. So that's a good thing to remember, because that's going to generalize very well to 2 dimensions, 3 dimensions, triangles, etc. And there's a reason for it, too. So here's let's say we're in 2 dimensions now. I want to find the value of my function at some point in this box. And I'm going to call this point st, where s is the ratio of the distance along the x-axis, and t is the ratio of the distance along the y-axis. So again, the same principles apply, which are, my formula will be like this. And if I want to know the coefficient of every point, like for example, this is going to be a weighted sum of all the values on f1, f2, f3, and f4, but what should the weights be? So just like before, the weights are actually going to be, like the weight of f1 is actually going to be the area of the box opposite f1. And this makes sense because if this point starts moving closer and closer to f1, the weight of f1 should get bigger and bigger because we're getting closer and closer to f1 and we're getting farther from the other points. So, and this box will grow to fill the whole box. So the weight of a point is the area opposite that point. Same here, the weight of F2 is the area of the rectangle opposite F2. And you can also derive this by doing linear interpolation in one direction and then another 1D linear interpolation. But it's easier to remember this formula is based on opposite areas or opposite volumes. So even in 3 dimensions, if we want to, the same rule applies. If I want to find the value of some function f by trilinear interpolation in this cube or in this 3-dimensional box, then again, I'm going to have this weighted sum of all the 8 different values at the corners. And then it's just a matter of finding the different weights on each value. And again, the weight is going to be the size of the box opposite that vertex. So here, for example, the weight of F2 is the size of that box. So it should be, if you look, it should be S and 1 minus U and 1 minus T. And here's the code for that. It looks exactly like the formula, pretty much. Okay. The nice thing is that this also applies, just the same idea applies to triangles. So since we're using simplicial complexes a lot in simulation, we have triangles, and if we want to linearly interpolate within a triangle, then we use what are called barycentric coordinates. And the barycentric coordinates are the alpha, beta, and gamma shown here. They're just the weights that we would apply to the function at the 3 vertices of the triangle. Same principle as before, which is the weight, any weight for a vertex is just going to be the area of the opposite triangle divided by the total area of the triangle. So the weight for the vertex B is beta, and it's the area of the triangle PCA over the area of triangle ABC. And same with the weight for C. It's the area of that opposite triangle. And here's just an illustration. Why does this make sense that it's the opposite one again? Because as the point moves closer to the vertex, that weight should go to 1. If the vertex where we're trying to find the value is directly on, or the point where we're trying to find the value is directly on one of the vertices, then it should just have a weight 1 while all the others have 0. So, for example, the barycentric coordinates for a vertex are just 1, 0, 0. So the barycentric coordinates for A are just alpha equals 1, and the other 2 are 0, and analogously for the other 2 vertices. Oh, that's wrong drawing there. Okay. And along the edges of a triangle, the barycentric coordinates, one of them is 0, and the ones associated with that edge are just linearly interpolated. So here, alpha is 0, and over here, the coordinate associated with B, beta, is 0. Okay, and barycentric coordinates can also be used for inside-outside tests. So if they're all positive, then we're inside that point is inside the triangle. Whereas if I have a point that has a negative barycentric weight, or more than one negative barycentric weight, then it's outside the triangle. And in that case, that area actually will be negative if I'm careful about signs. So we're actually talking about signed areas here. So that's linear interpolation. There are also higher order interpolation methods. Like if I have these 3 black points, I could do linear interpolation between them. But you could imagine that might not be very nice for, let's say, animation or something. If I'm going to create a path for an object or character, then we don't want them to move in this very discontinuous way. So we might do a smoother kind of motion, use higher order interpolation. There are different ways to do polynomial interpolation. There's a little bit more detail about that, but also references in our notes. And there are many other ways to deal with collections of points or function samples. So we might want to use different kinds of curves to approximate a collection of points, like Bezier curves, splines, or related surface patches. Also, when it comes to especially character deformations, there has been a lot of work on different coordinates or different ways to basically assign weights throughout a volume that have better properties than, for example, the barycentric weights that we saw. Okay. So now I want to talk to you a little bit more about finite differences. The equations that we see have a lot of spatial derivatives in them. So what do I mean by spatial derivatives? Well, we have time derivatives in these equation, like here's this time derivative, u sub t. But these terms, these are all spatial derivatives. So they're derivatives with respect to x, y, and z. And to discretize our spatial derivatives, we're going to look at finite difference methods. Okay. And so as Adam was mentioning before, kind of to repeat here, if we start with a definition of a derivative, and instead of taking this limit as h goes to 0, we're going to fix some finite h and say that we can approximate this derivative of a function with respect to x by taking a nearby point, evaluating the function there, and then basically looking at rise over run. So here's our rise over run. So that gives us this slope, which you can see is kind of close to the slope we're after, this one right here at that point. This is called a forward difference. Now, when we're talking about finite difference methods, we care about the order of accuracy of the method. We don't really need to follow this right now. There's more in the notes on this, but basically you can analyze order of accuracy using Taylor series and other methods, but Taylor series is a really common one. And if we do that, we can kind of arrive at an understanding of what our error is. So here, for example, for our forward difference. So we can see that the forward difference is exactly equal to the derivative plus some terms that depend where the dominant term is order h. And that's what we call a first order accurate method. So if we just use this expression to approximate f prime here, that means we're making this error because we're ignoring all these terms. So we're making an order h error. So what does that tell us? Well, it tells us that if we take our mesh and cut it down into be half, all of our grid, our grid mesh width to be half as big, we're going to cut the error in about half. Okay, so it gives us a sense of how much we can gain from doing more work. Okay, and now this was forward. The first one is forward difference. I look at a point to the right and take the difference of the functions there. I can just as well use a backward difference when I take a point to the left and look at the slope from there. So notice they give me different slopes. Oops. Okay. So they give me different slopes, but they both give me a first order approximation. Actually, if I take the forward difference and the backward difference and I take their average, then I get this formula. It's called the central difference approximation. And interestingly, now I'm actually you can see I'm taking data from 2 points that are farther apart. They're actually 2h apart now. But the order of accuracy of this method is actually h squared. So this is called a second order accurate method. So what's so nice about that? Well, if we think about, if we start with some h, and then we cut it in half. So now we have h over 2. Well, if you put h over 2 into this error term, h squared, so h over 2 will be, and you square that, that's h squared over 4. So when you cut your discretization mesh width by 2, your error will go down by approximately 4. So that's a big gain. And so with higher order methods, we can sometimes get we can often get much smaller error for a similar amount of cost. We do have to pay a little bit more in cost typically, but we can get this smaller error. Of course, we have to care about the constants, because this is an order h squared, so the constants matter too. Okay. Now, there's another thing about discretization error, which is when we can talk about the order of accuracy of it. And that gives us a sense of how much error there is in this discretization. But there are also qualitative things about discretization error. So if we look, for example, at forward difference, and if we look at what the discretization error looks like, it looks something like this. This is that order h term. It's h over 2 f double prime. And then there's other terms that depend on h squared, and so on and so on. Whereas over here for central difference, here's our error term, our first error term, h squared over 6 f triple prime. So these are sometimes important to know about, too, because they affect the qualitative behavior of the method. So in this one, our error is like f double prime. That can sometimes lead to what are called diffusive errors. Over here, we can have other types of errors that show up in our scheme. So these actually lead to qualitatively different errors, and we can actually see that sometimes in our schemes. And we can also construct higher order derivatives from finite difference with finite differences. Let's say I want to approximate f double prime, the second derivative of f at this black point. So I might say, okay, I'll use central difference of the first derivative of f. So if I take f prime at x plus h minus f prime at x minus h and divide by h, that's the central difference on f prime. And then I need to approximate f prime, so I'm going to use central difference again. And now I've got this expression that it just has values of f in it and h. And if I rearrange that a little bit, I get this. So I have the point on the left, the point on the right, and then minus 2 of my point at f of x divided by h squared. So this type of discretization is used quite a bit. So we'll actually give it a name here. And this is a 3-point stencil. So we sometimes talk about the stencil of a finite difference method. And what the stencil is it's basically this picture right here. So these 3 dots, black dots connected by the black line, that's the stencil of the method. It tells us kind of which points we're sampling around our point where we're approximating the function. It shows us which points we're sampling. So we're sampling to the left and to the right and at the point itself. And since we have 3 points here, that's why it's called this 3-point stencil. Now this Laplace operator, this triangle here, Laplacian, and in 2 dimensions, this is what it is. It's the partial derivative of the function with respect to x, second order, and same with plus with respect to y, second derivative with respect to y. So we can use, this is like f double prime, so we can use that 3-point stencil, so we get these 3 terms here for the x part, and we can do the same thing for y, we get these 3 terms. And this is a discretization of the Laplacian if we add those together. So here it is added all together, and now I've switched from x plus h, I've switched to call that instead using ij notation, so index notation. So this is one cell to the right. This is the center cell right there, ij, and then we have one cell to the right, one cell to the left, one cell up, and one cell down. So that's now I have this stencil for this finite difference method. It samples from these 5 different points, the point at which I'm trying to evaluate the function, and my left and right neighbors and my top and bottom neighbors. And in 3 dimensions, you can imagine we can extend this by adding the derivative in the z direction too, and have our 7-point stencil. So now let's actually apply this excuse me, to discretize what's called the Poisson equation. Poisson equation in 1D is this equation right here. It takes the second derivative of my function with respect to x is equal to some function. And then this is my domain, omega, so it's from here to here. And then my boundary of my domain is just this edge and this edge. And I need boundary conditions there for this equation. So these are given as the function u takes on some given data u bar at the boundaries. So how do I go about solving this? Well, let's say that we discretize our domain by sampling these 8 points on the domain. So now all the interior points are unknown. The boundary points are known because they're given by this boundary data. So at each interior node, I'm going to use my finite difference formula to approximate this second derivative, and I'm going to set it equal to the function value, which I'm given. And then at the boundary nodes, I'm going to use my boundary data. So this gives me an equation for u1 through u6 from here, and then when I'm discretizing u1, I'm going to need its left neighbor, u0, and so there I can use the boundary data. And when I'm discretizing u6, I'm going to need its right neighbor's value, and there I'll use that boundary data. And so I get 6 different equations, and I have 6 unknowns, u1 through u6. And here are my unknowns. And now this is coming directly from that 3-point stencil. So -2 is multiplying the unknown, and +1 for its left neighbor, and +1 for its right neighbor. And so that's one equation. And then it's the right-hand side of the equation over here, and then my 1 over h squared, pull that in front. So these u1 through u6, their values are all coupled together, and you can see that in this linear system. We get this linear system. How do I know their values are all coupled together? Because there's these off-diagonal terms. So off-diagonal terms in a linear system means this value is coupled to that value. And this value means this value is coupled to that value, and so on. So this gets solved all together for the unknowns U1 through U6. Okay. And now pass over to Adam.
It's almost time for a break. Let's see, so finite elements. With finite differences, as you just saw, we actually discretized the derivative. What finite elements do is they discretize the space of functions that you can represent. Okay, so the method is basically this. We discretize the space into a set of finite elements. Then we choose basis functions over the elements, and typically this is piecewise linear, though people have explored higher order basis functions and other basis functions. Then we do what's called a Galerkin projection onto these basis functions. So the problem we want to solve, we project into the space of functions that we can actually represent, and then we solve the problem exactly in that space. Okay, so whereas with finite differences, we had some equation we wanted to solve, and we took derivatives, and we discretized those derivatives that were showing up. Here, what we do is we take the problem we want to solve, the equation we want to solve, we project it down into a space of representable functions, and then we solve in that space. And so all of the error we incur occurs when we do that projection. So let's try an example, linear finite elements for elasticity. So we choose a type of element, and we're in 2 dimensions here, so we'll choose a triangle. Then we choose basis functions, and we'll choose piecewise linear. Then we project the deformation function onto the piecewise linear function space. So we had this deformation function, remember this from earlier? X of u is equal to x of u prime, or the initial u, plus f of u minus u naught. So when we project this down into a linear space, what we're basically saying is f has to be a linear function. And then we solve the problem. So we know we can compute forces from F, but how do we compute F? And this is the F in x of u equals x of u naught plus f of x u minus u naught. So let's look at some point u in our original triangle. What we'll do is we'll draw vectors along the edges. So this is a vector from u0 to u1 and a vector from u0 to u2. And we can then say that the point u is going to be u0 plus alpha times u1 minus u0 plus beta times u2 minus u0. So we have barycentric coordinates, though just a different representation. Instead of having alpha, beta, gamma, we just have alpha and beta now. And we can write this in matrix form like this. All we've done is to assemble this into a simple matrix. And then we can take a look at the triangle in world space. We do the same thing. We draw vectors along the edges. And we can express this point x as this in barycentric coordinates. And then we can assemble this into a matrix. And here, I'll make the point that x10 is a column vector. So this is a 2 by 2 matrix. And then we have a formula for u, and we have a formula for x. And then we can write that x of u is going to be x0 plus our x matrix here, times our u matrix inverted, times u minus u0. And when we take the gradient of this deformation f, this is just this matrix x, 1, 0, x2, 0, times x10, x20, minus 1. And so to break this down and take a step back, finite element methods sound like they might be a little bit intimidating. But actually all we're doing is drawing vectors along edges, taking the inverse of a matrix, and then doing a matrix multiply. It's actually quite simple to program. And another view of this is that we're mapping from the rest or material space to canonical space, which is when we multiply by that inverse basis matrix. And then we're mapping from canonical space to world space when we multiply by the world matrix. Then we solve the problem, right? So we say that the strain is going to be this strain metric that we talked about earlier, the co-rotational strain. We say that the stress is going to be some function of that strain. Then we say that the forces are going to be that rotation from the co-rotational form times the stress times the normal of the opposite face. And yeah, the normals are the normals to the opposite face in rest space. And then we have forces. And when we have forces, we apply those forces and use temporal integration to solve the problem further. Yeah, okay. So temporal integration. So there's explicit integration. There's two types of temporal integration we usually consider, and that's explicit integration and implicit integration. So explicit integration, we have some explicit formula for time t plus 1 in terms of quantities that were known at t. So this is our old friend, the Euler integrator, where we've expressed the position at time t plus delta t in terms of the previous position of t and the previous velocity of t. Everything on the right-hand side is evaluated at time t. I want to take a step back before talking about implicit integration and talk about choosing your integration scheme wisely. There's two techniques to get good accuracy out of Euler methods. And you sort of might remember these from, I guess, calculus when you were looking at the area that was under a curve. When you would just draw a box and up to the curve and go left or right, and then draw another box and go right, and draw another box and go right, that sort of corresponds to forward Euler. If you remember, though, you had other techniques that were a little bit better, and there were two of them. One was the trapezoidal rule, where you sort of created these little trapezoids, and those fit the curve better, right? You can see it right here, that fits the curve better than the forward Euler, so you're going to get a better approximation. An equally good approximation can be obtained using what's called the midpoint method, where you sort of draw your box so that the middle of the box intersects the curve rather than either of the ends. So here's the trapezoidal rule for tracing a particle through the velocity field. So we have this particle, this blue particle. What we do is we take a step, this is the velocity direction that we have at that particle. Then we take another step from the velocity field in that we measure the velocity at that point after we've taken a step. And then we average those two velocities, and then that's the step that we take. So we get sort of a nice average of two velocities, and this corresponds to the trapezoidal rule. For the midpoint method, what we do is we go just a little bit we measure the velocity direction. We then go just a little bit in that velocity direction. We measure the velocity there, and then we use that velocity to move our particle. Okay, both of these techniques are second order accurate. They're second order Runge-Kutta methods. They have exactly the same local truncation error, the same order of accuracy that we were talking about earlier, but they actually have very different behavior. The trapezoidal rule is smoother and more damped looking. The midpoint method keeps more energy, but can look sort of noisy and aliasing. And so it really depends on the problem that you're considering, which technique you'd like to use. There are times when you'd rather use the trapezoidal rule, and there are times when you'd rather use the midpoint method. And it's important to know that there's differences even beyond just the order of accuracy of methods. So let's look at position updates for our second order finite difference, second order ODE. There's three position updates that we could use. The first one is just the forward Euler, evaluated at time t. The middle one here is sort of an average of the velocity at the beginning of the time step and the velocity at the end of the time step. And then the third one is just taking the velocity at the end of the time step. It turns out that the middle one is second order accuracy because we're taking this average, right? And in fact, the second one, you can get the second order accuracy for almost no additional cost. But it turns out that in most cases you want to use that third one and sacrifice the accuracy because the third one behaves better in practice. The third one's known as symplectic Euler, and it almost always leads to better results. In fact, you can show that the second one, for problems that are just elastic problems, is unconditionally unstable. It's guaranteed to blow up. Okay, so now let's look at what we call stiff problems. So we'll consider a simple initial value problem where we're given a velocity and a position to start with, and then we have f equals minus kx. After one time step, the position is updated to 1 minus delta t squared k over m. And if delta t is greater than 2m, the square root of 2m over k, the spring will be more extended than when we started. And this is what we call a stiff problem. Well, for certain time steps, this is what we call a stiff problem. If the spring is extended more than when we started, then after we take another step, it'll be even further extended, and then even further extended, and eventually it'll end up being at infinity. And that's a bad state to be in, and this is what we say when we say a system goes unstable or blows up. Well, the way that we combat this is with implicit integration. So if we want to take bigger time steps, we turn to implicit integration. We replace the pair of equations that we had for explicit integration, where we were evaluating our forces at time t, with implicit integration, where we're evaluating our forces at time t plus delta t. Okay, I'm going to do a little math here. We'll get to the punchline in a second. So here's our system for our soft bodies. We linearize this system first, so we just make it completely linear. And then we take a look at this, the implicit integration that we want to solve. So x of t is described not in terms of things that we know, right? We don't know v of t plus delta t. We're describing our solution implicitly in terms of t plus delta t. So then we'll do some substitution, and we get that the velocity at the new time step is equal to the velocity at the old time step plus delta t times m inverse times the forces that are going to be at the new time step. We rearrange the system a little bit, and we get something that looks like this. I think the next slide, yeah, so this is just this. So this is a linear symmetric, a linear system. It's sparse and symmetric and positive definite, which is nice. Positive definite systems are what we want when we look at linear algebra techniques. We have a momentum term over here, and then we have sort of an Euler step with elastic forces and external forces. So this k times the displacements there, that's basically an elastic force. And then we have our external forces, and we're multiplying by dt, so sort of stepping them forward. So we can think of this right-hand side of this big linear system as being a forward Euler step without damping forces. And then we have a linear system on the left. And when we talk about code, we'll actually look at code that actually solves this big linear system. And then with that, I'll turn it back over to Tamar to talk about constraints.
Thanks, Adam. All right, so now we're going to switch gears and talk about these constraints. So this is a little bit different than when we were talking about F equals ma. So in F equals ma, we characterized all the forces acting on a particle, and then we integrated the state of that particle forward based on those forces. But sometimes the forces in a system can't be explicitly described without actually knowing all the other forces. So instead, we have a geometric relationship that has to be satisfied. Now, I've given a couple examples here. So we have this ball resting on a surface. And as we saw before, gravity is pulling down on the ball, but the ball is not going to go through the surface. The surface is going to push back up on the ball with a force that cancels the force of gravity. So in this case, we know that that force is mg. But what if I apply an even greater force on the ball? So not just gravity now, but I'm pushing down on it. So what's going to happen? Well, the ball's still not going to go through the surface. So that means that the surface actually pushed back even harder on the ball to counter the force I applied. So that means that the force from the surface really is depending on the other forces that are being applied to the ball. And what I really have here is a constraint that says the ball can't go through the surface. And there's going to be an associated constraint force, but it's going to be not something I can necessarily write down exactly what that is. It's going to be whatever is needed in order to make sure the constraint is satisfied. I've drawn another type of constraint on the right here. This is a joint constraint. So we have two rigid bodies that represent maybe two bones in a skeleton, and then there's a joint between them. For example, a joint like an elbow that's at the elbow or at the shoulder or at the wrist. And so this constraint says that the two bodies have to remain in contact at that point, but they can maybe rotate about that point relative to each other. So as I mentioned, the constraint forces they're forces that arise in response to other forces in order to maintain the constraint. Now, when we talk about constraints, we often think about the degrees of freedom. If I just have these 5 particles that can move freely, then I'm going to have 3 times 5 degrees of freedom in 3-dimensional space. Or if I have n particles, I have 3n degrees of freedom. And if I add constraints, what I'm implicitly doing is removing degrees of freedom. So in that drawing, for example, on the left, if I have these 5 particles, 3 of them can move completely freely, so that's 9 degrees of freedom. And then if I look at the pair that's now connected by a constraint, I can count degrees of freedom like this, for example. I can say, okay, well, one of the particles can move freely still. I can put it anywhere I want, so that's another 3 degrees of freedom. But now the other one that's connected to it, it can no longer move completely freely. It has to stay connected. And I can move it anywhere around the one that it's connected to. I have 2 choices now. So I've actually lost 1 degree of freedom from that constraint. And we saw before with the rigid body, regardless of how many particles it's made up of, if I put the constraint that every particle stays a fixed distance from every other particle in the rigid body, I reduce all of the degrees of freedom in that body down to 6 in 3 dimensions. Constraints can be unilateral or bilateral. So on the left is a unilateral constraint, and on the right is a bilateral constraint. Unilateral means one-sided, and that shows up as an inequality. So a constraint has an equation associated with it that describes the geometric relationship that we want to satisfy. For the case of a unilateral constraint or a one-sided constraint, it's not an equation, it's an inequality. So this one says the ball is not allowed to go into the surface, but I am allowed to pick it up. So it doesn't have to stay connected to the surface. I can lift it up, but I can't push it down. So it's one-sided or unilateral or an inequality constraint. On the right, those 2 bodies have to stay connected at that point. They can't come together at that point, and they can't move apart at that point. So it's constrained to be an equality there. And so that will look something like g of x and t, where time equals 0. And here's specifically what those 2 examples might look like. There's other ways we could write them too. So on the left, the height of the ball is constrained to be greater than or equal to h. So if I move everything over to the left-hand side, that's y1 minus h is greater than or equal to 0. And on the right, the 2 points on the bodies, x1 plus r1, is constrained to be the same as the point x2 plus r2. So I can, if I move everything over to the left-hand side to get a 0 on the right-hand side, it looks like that distance between those 2, or the vector between those 2 points has to be 0. Okay, now, generally, when we say constraint, we really mean a hard constraint, a condition that needs to be satisfied. But we can also soften our constraints, and then we call it a soft constraint. So when it's for a soft constraint, we'll say, well, we want those 2 points on the body to be touching, but we're not going to make the force arbitrarily strong to counter any other force in the system. We'll actually just put something like, it acts kind of like a spring, or maybe a damped spring, or something else, but we'll put a restoring force that will try to bring the points back together if they get pulled apart. It will try to satisfy the constraint, but it will limit how strong it can be. It won't be arbitrarily strong. And so that's a soft constraint. And in that case, the constraint won't always be satisfied. It has to compete with the other forces in the system. So we'll see a little bit of error in that constraint sometimes. On the right is a hard constraint. That means we're going to make the force as strong as necessary to counteract all the other forces so that those two points are actually satisfying the constraint, or so our constraint is maintained. So there are different ways to approach problems that have constraints in them. So if we have F equals ma, or dynamics, along with some constraints, we call that a problem of constrained dynamics. The solution methods fall into 2 broad categories. These are called maximal coordinates for the first category, and the second category will be called generalized coordinates. Maximal coordinates is what we're used to thinking about, kind of here's a point that we want to simulate its dynamics, and its coordinates are x and y. This is just the mass attached to my pendulum. So this is maximal coordinates. How might I formulate this problem? Well, I'll say I have F equals ma, and that particle, its coordinates are x and y, so its accelerations are x double dot, y double dot. And then the forces acting on it are going to be gravity and a constraint force, F sub c. That's the force that's going to arise in reaction to the gravitational force to make sure that the particle stays on that circular arc connected to the pendulum. So that represents like the tension in the connection. So that's the maximal coordinate view on the left. On the right, you can also formulate certain problems with constraints using generalized coordinates. Instead of using x and y, we observe that actually this problem only has 1 degree of freedom. And we can describe that degree of freedom as the angle that the pendulum is making with a vertical. So the pendulum's going to swing back and forth, and if the mass stays connected by that fixed length L, then really the only thing that's going to, we note one number, to describe the state of the system. It could be the angle with a vertical. So it's also possible to write down evolution equations directly for that 1 degree of freedom, theta, and they'll look like what I've written down here, theta double dot plus g over L sine theta equals 0. So this equation can be derived using the analytical mechanics frameworks that I mentioned earlier, but I won't go very much into depth into those. And these two approaches should give us the same dynamics, though they are mathematically equivalent, but numerically they could be very different. In fact, we'll talk about how they can be different. So mostly I'm going to talk about approaches that use maximal coordinates, so sticking with this x and y and having to actually find the constraint forces and enforce those as well. In penalty methods, we treat the constraint as soft, and in penalty methods, we use F equals ma, and we just have to add another force, and that's the penalty force. And here's an example of what it might look like. Looks a lot like a spring force. It's a restoring force that acts to counteract any violations of the constraint. But this is a very simple example where we just have some constant k times the violation in the constraint. We can also have other terms like damping terms that react to differences in relative velocity of those 2 points. And that can actually help to better enforce these in a penalty method. So penalty methods are nice because they're very simple to add to a solver. You can see above here, all I had to do was just add a new kind of force. If I have a solver where I know how to solve F equals ma, now I just have another type of F in my system. It's just penalty. So that's simple. The drawback is that we have to tune this parameter k. So you look at this equation up here, there's this minus k in it. That's kind of the strength of my penalty force. And it's not a physical parameter, because physically I actually want this constraint to be satisfied. So I have to kind of say, what should I make k be? And I have to pick a value for k. So you want to pick k to be strong enough so that this constraint is enforced. It'll depend on all the other forces in your system. And this can get kind of complicated when you have many different constraints in your system, and you have to pick these stiffness parameters for the different constraints, and they compete with each other. And it can become difficult to tune these parameters. Generally, we don't really like to have too many parameters in our simulations that are non-physical parameters. Physical parameters are fine. We can possibly look up a value for them for the material we're trying to simulate, but non-physical parameters, we don't like to have too many of them. Another thing is that if we really want this constraint to be well enforced, we might have to make k kind of large. And we might end up introducing forces into our system that are stiffer than the ones that we otherwise have in our system, and creating this stiff problem that forces us to take either very small time steps or to switch to implicit integration. Penalty methods also are not going to strictly enforce a constraint, so we'll see constraint violation. So if you're using a penalty method, you have to accept some amount of constraint violation. And it's the spring-like force, so you might actually also see some oscillations in your constraint. Another type of approach falls under the category of Lagrange multiplier methods. So in Lagrange multiplier methods, we're going to try to actually estimate the constraint force that we need in order to counteract the forces that are trying to violate the constraint. To find this unknown constraint force, we add unknowns to our equation that represent the strength of the constraint force. And then, since we've added unknowns, we need more equations. Those equations are our constraint equations, or maybe differentiated versions of those. So let's take a look at some abstract things about a constraint. So we have our particle or configuration of our system represented by x equals, and has all these components x1 through xn. And our constraint defines some relationship between those components that we want satisfied. So abstractly, we can think of our constraint, g of x equals 0, as what's called an implicit surface. What's meant by implicit surface? It's called implicit because the function that we have to describe it, g, is a function where we plug in a value of x, And if we get 0, we say, okay, oh, x is on the surface. And if we plug in a value of x, and get something less than 0, then we're on one side of the surface. If we plug in a value of x and get something bigger than 0, we're on the other side of the surface. So this function g of x implicitly defines a surface, which is the values of x for which g of x is 0. An important quantity in constraint mechanics and these Lagrange multiplier methods is the gradient of the constraint. So the gradient of the constraint is equal to the vector whose components are the derivatives of the constraint equation with respect to each variable. So there it's listed dg dx1, dg dx2, etc., up to dg dxn. And it has a geometrical significance, or geometric significance. The gradient is always going to be pointing normal to the constraint surface. So I've drawn that as a picture there. And therefore, it's going to be perpendicular to a tangent to the surface, which I've labeled z. So z is tangent to the surface, and gradient of g is normal or perpendicular to the surface. And the physical significance of this is that we can now talk about the constraint force and what directions it's allowed to point. So if a constraint force is, most constraint forces we care about, we want them to be what's called workless with respect to directions that don't violate the constraint. Now we can write that mathematically as the constraint force dotted with a tangent vector z has to be equal to 0. In other words, if the constraint force is perpendicular to z, then it's going to point in the same direction as the gradient. So if the constraint force points in the same direction as the gradient, then we can write it down as constraint force is equal to the gradient scaled by some unknown value. That unknown value is often labeled lambda, and it's called the Lagrange multiplier. It represents the strength of the constraint force. Let me make that, one comment is, instead of gradient, I'm going to use this J notation for Jacobian, so that we can, when we generalize this to multiple constraint. But J here is just the transpose of the gradient. So if I want to get my gradient, I'll just write it as J transpose. That's the gradient. And my lambda, so I'm going to use that notation. So physically, what does this workless thing mean? Well, it actually makes a lot of intuitive sense. I have this constraint force, Fc, arising to prevent the block from falling into the surface. So I don't want my block to go through, let's say, the table. So Fc is the constraint force pushing it out so it doesn't do that. Now, it would look very weird if the block started sliding sideways, right? You don't expect that to happen. If you have a block resting on a table, it's going to, look kind of funny if it starts inching to one side. So that would mean my constraint force was actually doing work in a direction that's not violating the constraint. My constraint force is only allowed to do work in directions that are trying to violate the constraint. If there's some force trying to push the block left or right, my constraint force, generally if it's a workless force, it's not allowed to counteract those forces, because those forces aren't trying to violate the constraint. So the physical meaning of being a workless constraint is it only acts in directions that are actually trying to violate the constraint. And that's why we can say that it's going to be parallel to the gradient, because the gradient is trying to take you off the constraint surface. So the constraint force will try to push you back on. Now there's an important exception to that, which is friction. Friction, when we have sliding contact, like a block sliding down a plane, there's going to be a constraint force that prevents the block from going into the plane. But as a block is sliding down, the force that prevents going into the block will also be associated with a frictional force that arises that damps the motion of the block. So the friction is associated with a constraint force that is doing work in the tangential direction to slow the block down. That's the main exception that we will have to worry about. So how do we actually solve these constrained dynamics equations? Well, we know our equations look something like this. So we have F equals ma, and there's also going to be this constraint force in our net force, which is going to look like the gradient times some unknown. And then we have lambda as an extra unknown, so we have an extra equation, the constraint. And what's typically done is that in order to solve this, is called a differential algebraic equation, because it mixes differential equations and algebraic equations. In order to solve this, make it easier to solve this, usually the constraint is differentiated. So we start with this constraint g of x equals 0. It tells us what valid configurations or positions in our system are. And then we can differentiate it with respect to time. I'm using dot for the time derivative. So I'm going to do ddt of g of x. So I apply the chain rule, and I get dg dx, or the Jacobian, or that gradient. And then the chain rule tells me dx dt, that's the velocity. So differentiating the constraint once, I get that second equation, which is that the Jacobian times the velocity must be 0. And differentiating it once again, I get an expression for what are valid accelerations. So I apply the product rule to this, and I get j dot v plus j v dot, which is a, equals to 0. So these two additional equations came from our original constraint equation, and they're also valid equations. Mathematically, they should hold, because we are just taking a time derivative of our original equation. So we still have a true equation. And they tell us something about sort of legal position velocities and legal accelerations. So to solve this system, instead of using the original constraint equation, we'll use a twice differentiated one here. And now we have acceleration in both. So now we've reduced this to from a differential algebraic equation to an ordinary differential equation. And reorganizing this, putting my unknowns, the acceleration and lambda, into this vector, I can write this as this system. Mass on the diagonal multiplies the acceleration, and then I have the equations for the first set of equations is my f equals ma, and the second set of equation is my differentiated constraint. Okay, so this is the structure of this system comes up a lot in constrained dynamics. It's called a KKT system for Karush-Kuhn-Tucker. It also comes up in constrained optimization problems, which you can very closely relate constrained dynamics to constrained optimization problems. So this system, actually, it's very interesting. It comes up also for fluids, where our pressure is our Lagrange multiplier. And generally, it's not always that easy to solve, but it's very important physically. We can generalize this really easily to multiple constraints. Now I have m different constraint equations. So you can think of my skeleton, and it has all these different joints in it. Each one of those joints has a constraint equation associated with it. So I can put all those together into this vector of constraint equations. And the constraint force is basically going to be a set of constraint forces, one for each constraint. Just like before, I'm going to have the gradient for that constraint multiplied by some unknown lambda. But since I have m constraints now, I'm going to have m different Lagrange multipliers, lambda 1 through lambda m. And my system looks just like before, but now there's going to be more unknowns in A, more unknowns in lambda for all of the different unknowns and all of the different constraints. Okay, and we'll come back to how to solving this system in practice. Now I mentioned that in addition to maximal coordinates, there's also this other approach based on generalized coordinates. In generalized coordinates, I'm not going to talk too much about those, but just a little bit about them. We have to figure out what we want the generalized coordinates to be. So for the pendulum, we described this angle theta. Sometimes the hard part of the problem, if you're using generalized coordinates, can actually be trying to figure out how to describe your system in a way that doesn't have the constraints in it anymore. So if I'm just talking about theta now, then I've kind of absorbed the constraints into my representation of my problem. And it's nice because I don't have to worry about the constraints anymore. I can just simulate theta in a completely unconstrained way, and I'm satisfying the constraints. So they're getting built into the problem formulation. But it's not necessarily obvious how to find the right set of generalized coordinates. And for some constraints, it's actually theoretically not possible. The constraints have to be what's called holonomic to be able to be represented this way. So our most common example of generalized coordinates that's used is just a rigid body representation. It's a type of generalized coordinates. Instead of using describing all the particles on the body and all the forces between them and all the constraints between them, we take that and just use position and orientation. So that's a form of generalized coordinates. And we also had our pendulum here. And deriving the equations of motion for the pendulum, you have to go through a few steps to define how do you transform between maximal coordinates and those specific generalized coordinates. And you can use something called the Euler-Lagrange equations to get this equation for theta. Okay, so now I wanted to talk to you a little bit about practical constrained rigid body systems. So there are different types of constraints that come up when we're simulating a bunch of rigid bodies together. A common one might be having joints between rigid bodies, and these are called articulation constraints. So here's my skeleton in front, and every different joint has an associated articulation constraint. And there's going to be different ones. For example, my elbow just has 1 degree of freedom. I can only rotate, So let's say my knee has 1 degree of freedom, whereas my shoulder has 3, I think. So there are different kinds of joint constraints. We also are going to have collisions between rigid bodies, and we'll have resting and sliding contact. So you can see this stack of blocks that might just be at rest. So right here. So getting this right actually might seem trivial, but in a dynamics simulation, it can actually be non-trivial sometimes to get this right. What you might see if you don't get it right will be that the boxes will jitter around. They'll keep undergoing collision with each other, and instead of having a nice, steady resting contact, they'll jitter. Over here, I might have this block sliding down, so that's sliding contact. So actually, we wrote down that KKT system for acceleration and Lagrange multipliers. But it turns out that when you're solving such a large system for rigid bodies, you can get problems with that acceleration level formulation. It doesn't actually work well with rigid body systems, and you can actually set up scenarios where there's no solution. And instead, you get better results if you're using a velocity level formulation. So instead of differentiating the constraints twice and getting to a rule for accelerations, we want to just differentiate once and use the rule for velocities. And so in order to be at the same level with the dynamics equations, we look at our dynamics equations in impulse momentum form. So if you take F equals ma and integrate over some small time from t1 to t2, then over on the left, you get the mass comes out, and you get the velocity at time 2 minus velocity at time 1. And on the right, you get this quantity j, which has units of time times force, or impulse. So here my integrated semi-discrete F equals ma, my equation, my dynamics equation. So it relates the velocity at time n plus 1 to the velocity at the previous time step, the forces in the system, and my constraint forces. And since these are now integrated, I replaced lambda with mu. So mu is lambda times dt, some small time increment. And the system looks very much like before. Here it is with the mass, and these are the Jacobian of the constraints. But now I have velocity instead of acceleration, and mu, which is very much like the Lagrange multipliers, but just multiplied by some time. And my right-hand side. Now I can also do block Gaussian elimination on this to eliminate the Vn plus 1 velocity and get an equation for mu n plus 1, and then it will look like this. Now, one of the differences between this equation and using this formulation, this one is what's called very sparse. Typically, so your mass matrix is sparse, and also your constraint Jacobians will be fairly sparse, because usually a constraint, it doesn't relate every object to every other object in the system. Usually it just relates maybe a pair of objects to each other, or maybe a few objects. And since it's only relating a few degrees of freedom, typically, what that means mathematically is sparsity. Okay, but this is a product of these things. We lose sparsity. So now instead of doing that big global system that we just saw here, this J M inverse J transpose, instead of solving that, a common thing to do is something like the following. So we integrate all of our forces in time, ignoring the constraint forces, and we get this intermediate velocity v star. So we want to go from time n to time n plus 1. So we're not quite done because we have to add all the constraint impulses that will help satisfy the constraint. And now a common thing to do is actually to iterate this pairwise, the second step. And I'll show you how that might look. So after the time integration, my objects are now violating the constraints. So let's say I just had gravity here. And I'm illustrating this with positions, but this is just integration on the velocity. So it's really the velocity right now that's violating the constraint and not the position. But the velocity is telling me if I add gravity that I should go into this triangle when I know that will violate the constraint. So now I want to correct this. Okay, so if I solve all the system together, if I solve for my impulses globally, I can correct everything all at once. And that my state will go back to being like this. But a common thing to do is actually to treat this iteratively and to treat maybe pairs of bodies together. So for example, if I take first this block on the bottom, and I'm having a collision with the ground, so I'm going to find an impulse I need to correct that violation of the constraint and correct. So now, I don't know if you can see it, but it moved back up. But now that created a constraint violation with this block right here. So maybe now I'll correct that pair. And after that correction, now what happened is these two are not colliding anymore. But because of the correction, I moved a little bit back into the ground. Not as much as I was before, but I'm still now violating this again. So in this iterative approach, which is called the Gauss-Seidel approach, where I do one pair at a time, and then I do the next pair based on the state that I just arrived at from the previous pair. I would keep repeating this over and over, and until I reach some kind of tolerable level of error in my system, or maybe until I've done a fixed number of iterations, and still have maybe potentially some error. Okay, so why do I want to even do this iterative approach? If I do everything globally, then I need to solve a potentially large linear system. And remember I showed you that my contact constraints are actually these inequality constraints. They're not generally equality constraints because they're one-sided. I can lift something off a surface. And so when I have inequality constraints, what that leads to is a system that's a little bit more challenging to solve than just that KKT system. It's actually what's called a linear complementarity problem. And it has these complementarity conditions in it that say that either I'm separating or I can have a constrained force, but not both. It's easier to solve this iteratively, but the drawback of that is that it might be slower to converge. On the plus side, I can handle those inequality constraints pretty easily pairwise. Now, another problem arises when we use those velocity level constraints or acceleration level constraints. So the formulation we did discarded our original constraint equation. Instead, we used this differentiated form, either once differentiated or twice differentiated. And what happens is that if we're no longer satisfying the constraint on positions, only on velocities. So numerically, we're actually going to get drift away from our constraint. And what that would look like for our pendulum, for example, is here it is the exact thing. This mass should just keep going back and forth on this arc. But if we use a velocity level constraint enforcement, the velocities will be correct, but when I take these finite time steps, I'll step off. The mass will kind of step off of the constraint. Instantaneously, the velocity might be correct, but over a finite time step, it will come off the constraint. And so I'll get what's called drift, which can be visually disturbing in the simulation and may also be problematic for other reasons. And so to correct drift, additional things have to be done in our simulation, and that's called stabilization. So there are different ways to do stabilization. A couple of the main ways that are used are instead of just enforcing the velocity level constraint, we add back the position level constraint with some parameter here, gamma, which is kind of like that K in the penalty method. So this is sort of a mix of those. And if there's any actual drift, this will be non-zero, and if we're enforcing this, it'll act to restore that. This is called Baumgart's stabilization. Other things that are common to do are what's called post-stabilization, where you do another correction step to correct any errors that are in your position at the end, using a similar thing, using similar techniques as you did for your velocity, but now correcting your positions to get rid of that drift. Another thing that people noticed in practice was that this system behaved better if instead of a 0 here, they added some small non-zero parameter in this position right here. And what they noticed is that tended to soften the constraints. And we can also add stabilization in this formulation. And so systems like this are also common to see, where we have slightly softened constraints and they're also stabilized this way. This gives us better numerical properties to this system, and it can also get rid of problems with redundant constraints. But it does tend to add a little bit of compliance to the constraint to soften them a little bit, so you might also get a little bit of constraint violation. Okay, so I want to talk to you about more about collisions and contact. So we have a few different scenarios here that are challenging from the perspective of collisions and contact. Here's the Newton's cradle, a fun toy to play with, where momentum is traveling through the system through these collisions. And we also have some really complicated systems with a lot of different contacts, a lot of different collisions simultaneously going on. So to get a pile like this correct with your simulator, where you've resolved all these contacts, is quite challenging. And generally speaking, contact and collisions and constraints are one of the more difficult parts of a simulation. Just doing F equals ma is relatively easy, but getting all of those constraints, contacts, and collisions resolved makes it much harder. Collision processing, it can be looked at as two separate problems. One is collision detection, so figuring out that things are actually colliding, and the second then is collision handling or response or resolution to actually resolve that collision. So we're often dealing with polygonal representations of our geometry, and there are a lot of algorithms and theoretical results that apply specifically in this case, and in particular for convex geometry. So I just illustrated what's meant by convex or non-convex. So non-convex, if I pick 2 points in my object and draw the line between them, it might fall outside the object. That's non-convex. Whereas in convex, if I pick 2 points and draw the line between them, it's going to be completely contained within the object. So it's generally easier to deal with convex geometry. But we can also take non-convex geometry and decompose it into pieces that are convex, and then apply algorithms for convex collision detection. And other data structures that are useful in collision detection can be, for example, a signed distance field. So here we have this dragon, and a signed distance field for this dragon will assign a value, a scalar value, to every point in space around this dragon and inside this dragon. And this is, again, that implicit surface we mentioned earlier. So wherever this value is 0, that means we're on the surface of the dragon. If we're inside, it might be negative, and outside it might be positive, or vice versa, depending on your convention. And since it's a distance field, the value this function takes on will actually be the distance to the closest point on the surface. So these can be a useful function for collision processing or collision detection, because, for example, if I want to know, if I have this circle here and this signed distance function for this circle, and I want to know if this square is colliding with my circle, I can test the vertices of my square by plugging them into this function. And if the vertex gives me back, if I plug it in here and I get a negative value, I know I'm inside the circle, and I know I've detected the collision. Whereas if I take this vertex and plug it in here, I'll get a positive value, and so that tells me that vertex is outside. Sign distance fields are also useful because they give us more information rather than just in addition to inside and outside. Since it's the distance from the surface, it can tell me how deep inside the surface my object is, which can be used to decide how to handle the collision. And I can also use the gradient. Remember, the gradient of an implicit surface gives me a normal direction. So I can calculate numerically the gradient of this function to get a normal to find the direction that I want to push this object out of that other object. Collision detection is sometimes split into two phases, a broad phase and a narrow phase. So in the broad phase, we try to take this n-squared problem and prune it down. So if you have n objects and they're rigid, then you can have n-squared possible pairwise collisions. Every object might be colliding with another object, so that's n-squared. And that can be a lot of collisions to test. But if you use acceleration structures in this broad phase, then you can prune away a lot of possible collision pairs and get down to a smaller set to do more expensive tests on in the narrow phase. So different approaches that are used to accelerate collision detection are, for example, bounding volumes. This object has this complicated shape, and it might be kind of expensive to do collision detection against it. But we can first put a bounding box around it. This stands for axis-aligned bounding box. And we can have very fast procedures that test collisions with boxes. Now, if we test collision with this box and we find there's no collision, then we're done with this object, and we don't have to do more expensive tests against this complicated geometry. So that can accelerate things. We can also put these into hierarchies and quickly prune out large collections of objects at a lower level of our hierarchy before we descend into the hierarchy. Excuse me. I don't usually talk for this long. Okay, so these are hierarchical bounding volumes. Another thing that's common are spatial partitions, where we take space. Now, instead of making volumes around those objects, we partition space into different parts and track which objects are in which part, and that helps us prune out collisions that we don't have to check as well. So here's a uniform spatial partition and an example of something called a KD tree, which is used for often with collision detection. Collision detection can be either discrete or continuous. So if we consider, for example, this object, and we want to know if they're going to collide during a time step. So they're both very thin objects, and if we only test the object at the end of the time step, what will happen is, let's say this one's stationary, this one travels like this during the time step. So if we only look at the end of the time step, we'll say there's no collision because this object is not colliding with this object. But actually, during the time step, in order to get over here, this had to move through this object. So if we only do what's called discrete collision detection, we miss this collision completely because we just see the valid state at the end of the time step. And we don't. Instead, if we do continuous collision detection, then we actually take the motion over time into account. And we have to look at this whole volume swept out by the motion of this object. And then we detect that that volume does intersect with this other object. So we can detect that we did indeed have a collision. And we want to process that collision so we don't see objects moving through each other. As you might imagine, this continuous collision detection is more expensive generally than this discrete collision detection, but it's more accurate. So after we've detected our collisions, now we have to do something about them to respond to them. And that's these impulses, or these are the constraint forces that are going to correct the violation of the constraint. But at this level, we're thinking about them as impulses. And you might have done some calculations like this in a physics class if you have the collision of two particles. So the main principle we're using here is Newton's third law of action-reaction. So when these particles M1 and M2 try to collide with each other, this impulse arises, a pair of impulses, J and minus J, arises. And I'm going to apply j to the first particle, it's going to give me a new momentum m1v prime. I'm going to apply minus j to the second particle, and it gives me a new momentum m2v2 prime. So now I have, let's say these are one-dimensional, so I have 1, 2 unknowns, v1 prime, v2 prime, and another unknown j. So that's 3 unknowns, but I only have 2 equations. And so I need a third equation. And here comes my assumption about what kind of collision this is going to be. So I'm going to first look at this assumption, which is called a sticking collision or an inelastic collision. There's not going to be any bounce at all between these particles. So after the collision, their velocities are going to be the same. They're going to be traveling together. So now I have the same number of unknowns as equations, and I can solve this like I did down here, solve by expressing v1, divide by m1 on both sides, divide by m2 on both sides. Now I have an expression for v1 prime and an expression for v2 prime. I stick those expressions into here and solve for j. And once I've solved for j, I can go back to these equations and find v1 prime and v2 prime. And since it was an inelastic collision, they're the same at the end. And this is sort of, what I get is sort of an average of the velocities before the collision, but it's a mass-weighted average. So the more massive object will have a greater influence on the velocity after the collision. I can also do an elastic collision. So I replace that v1 prime equals v2 prime equation with this instead. This is an equation for an elastic collision. So this is the relative velocity of the two particles before the collision. And this is their relative velocity after the collision. And epsilon is a positive number between 0 and 1. And here we have a minus sign. So the relative velocity is going to flip signs after the collision. That makes sense because we want them to bounce off each other. So before the collision, they're traveling towards each other. After that collision, they're traveling away from each other. If we put in epsilon equals 0, we get what we had before, the inelastic collision. And if we put in epsilon equals 1, we get a perfectly elastic bounce where they're traveling away with a relative velocity that's equal to, in magnitude, to the relative velocity before. But we can choose this based on what we want, how the behavior that we want. So we can empirically choose this between 0 and 1. And again, we have the same enough equations and equal number of equations unknowns now, so we can solve and get our impulse and our velocities. If I have this deformable object, we can apply collisions. Use a bouncy ball, and when the ball hits the ground, the particles that are on the bottom of the ball are undergoing an inelastic collision with the ground. And we are solving these equations just like I showed you earlier, where we find an impulse j that applies to the particle on the ball and the particle on the ground. And the ground isn't moving, so we don't really care about that. Once we find the impulse j, we apply it to the particle on the ball. And now why are we getting that bounce? Because as these particles are prevented from moving into the ground, so they have a 0 velocity in the vertical direction, and then the rest of the objects keep falling on those particles. So what's happening is the ball is compressing. The ball is compressing down here near the ground. And that compression is going to cause elastic forces to try to fight back. So it's this rubber ball or something like that. The elastic forces are going to fight back and going to push back on the ball, causing it to bounce up. So we have to be careful here that we allow the particles that are on the ground to come off of the ground. And so we actually want this one-sided constraint again, where the particles are allowed to move off the ground so we get that bounce up in the air. Otherwise, the ball will try to stick to the ground, which is not what we want. So rigid body collisions are, physically, they're similar to deformable object collisions, but because we're doing this rigid body idealization, we are not going to be able to have a particle momentarily stick to the ground and then store deformation energy and bounce back up. So instead, what's done with rigid bodies are what are called algebraic collision laws for before and after the collision, very much like what I showed you for the inelastic and elastic collision where we find an impulse. But it's just a little bit more complicated, or actually significantly more complicated for a rigid body because we have to deal with both the linear part and the angular part. Specifically, what makes it much more complicated is the friction case. So we have three cases here. We have a case where the bodies just stick together after collision. That case, and then that's one case, and then we have two cases where we can bounce. One is no friction, and the other one is with friction. So we have these three different cases, and the significantly harder one is the one with friction. So first, if we look at the easier one, so here's a rigid body inelastic collision. So we want the bodies, we have this green body and this blue body, they're both rigid bodies. They're traveling toward each other, and then at some moment in time, we detect that they're colliding at this point here. So we want to find a pair of impulses, and the impulse is going to be applied, it's going to change the linear momentum of the body this way, of each body, and it's also going to affect the angular momentum. So for this body, it'll be R1 cross J, and for the second body, we'll get this change in momentum of R2 cross minus J, or minus R2 cross J. And since we're assuming sticking, this is the condition we have after the collision. It says that the bodies are moving at the same velocity at this point after collision. So right here, they're sticking right after the collision. So this gives us enough equations. We have 15 equations and also 15 unknowns. The unknowns here are 3, 3, 3, and 3 for the linear and angular velocity components. So that's 12. And then we have an impulse with 3 components. That's 15. So there's the 15 unknowns. And then equations, we have, these are each 3 equations because we're in 3D. So we also have 12 equations here. So we need 3 more. And this is the 3 more equations. Now, in a frictionless collision, they will not bounce, they will not be allowed to penetrate each other, but we will allow them some relative motion in the, we will allow this relative motion at the end of the collision. In fact, they'll bounce off each other in the normal direction. So this is very much like this is the elastic collision we saw previously. We're taking this 3-dimensional velocity. When we do the dot product with n, we're restricting the velocity that we're looking at to the component along the normal direction. So in the normal direction, we have a bounce, and the impulse is only allowed to be in the normal direction. So we've actually reduced the number of unknowns, because instead of 3 unknowns in the impulse, there's really only 1, because we're forcing it to be only in the normal direction, and there's just a scalar unknown now. So that's taken away 2 unknowns. And we have these 12 equations here. We have 13 unknowns, so and this is 1 more equation because we're projecting the velocities onto the normal component, so that's just 1 equation. Now the harder case of collisions with friction. A most common friction model that is used is called Coulomb friction, a model for dry friction, of the sliding of 2 materials past each other. So there's this empirical coefficient mu, the coefficient of friction, that describes the interaction of 2 materials, it describes the strength of the frictional force between them. And now in friction, we have to worry about 2 cases. One is we might have static friction. So you can imagine there's a scenario where this block is not sliding, it's just sitting there on the plane. That's called static friction. And in that case, we don't, the frictional force, this is F sub t. Now, there's 2 components of force associated with the contact. There's a normal force that's preventing the block from going into this. And there's a frictional force now, and that's in the tangential direction. It's going to oppose the motion of the block. So what's keeping this block from sliding down is the force of friction. And if the block is not moving, what we know from the Coulomb friction law is that the force of friction is going to be less than or equal to the coefficient of friction times the friction in the normal direction. Now, if we have the case of sliding, then we've kind of maximized the possible force of friction. It's as large as it's allowed to be. It's equal to mu times the normal force magnitude in the opposite the tangential motion. And at this point, we have sliding because the frictional force is not enough to counteract the other forces trying to pull it down the block. So this inequality is drawn like this, as it's called the friction cone. It says that the tangential force is allowed to be inside this friction cone or on its surface in the case of sliding friction. Another way to illustrate this is with this plot here, where this is the static case. So in the static case, I have no relative velocity, so I'm 0 along this horizontal axis. And there the tangential force is somewhere between the normal force mu n or minus mu n, Fn. Now in the sliding, where as soon as I am sliding, so as soon as the relative motion is over here or over here, my frictional force is kind of maxed out at being magnitude mu Fn. So an example of how to handle friction in this framework is from this paper. This is our elastic equation for the motion in the normal direction, an elastic bounce. So we might solve this first by assume that we're sticking. So we'll add these two other equations and solve and see what kind of impulse we get. And in particular, we'll check if the impulse we get from this assumption satisfies the Coulomb friction cone. If it does, we'll say, okay, we're done, we're sticking, we don't need, the force is small enough, so we're not outside the friction cone, so we have enough force to stick. But if the force is going to violate the friction cone, then we'll say, oh, it must be in the sliding case, and we instead have an impulse equal to this component in the normal direction, and then mu times that component for the tangential, and we solve with this, again, to find the actual frictional impulse. Okay, so this is actually, what we want to do now is switch gears, and Adam will show you some demos of a few basic simulators.
It's dark in here now. Okay, well, that's very readable. Good. Okay, so everything I'm going to show you is available on the website that we have for this course. If you scroll down to the very bottom and download the source code, you'll be able to get it. And if you look at what's in the directory, there's a simple array 3D that just makes indexing easier. All right, you want to get that web page? It's easy enough to find if you can remember my name. Okay, then we have an explicit FEM simulator. Then we have a fluid simulator. Sorry, explicit FEM, fluid simulator, implicit FEM, just a directory of sample inputs, some stuff to deal with JSON input type stuff. There's a makefile that works on Mac OS and should work on other operating systems pretty easily. I've already compiled this part. Then there's a simple viewer for the particle file that the fluid simulator outputs. And then there's a rigid body and a spring mass simulator. So I'll go ahead and compile all those now. And while those are compiling, I will pull open the Emacs window. Okay, so here's our simple particle simulators, spring mass simulators header file. We're not using very many special libraries. We have IOStream and vector and strings, but we are using eigen for all the code in here. So you'll need to get that if you want to play around with this stuff. I should mention all of this code is meant to be readable and simple. I sort of drew the line at what I thought was the simplest reasonable thing you could want to play around with. It is not super fast. It is not optimized. We erred on the side of simplicity over optimization. It also doesn't incorporate lots of fancy techniques. It's really just sort of bare bones basic stuff. Okay, so in our particle structure, we have a mass for the particle. We have the position, the velocity, and a force accumulator. And this should look like the code that we saw at the beginning of the course, actually. We have the rest length of our spring, and we have the two particles that are affected by the spring. So these are indices into the particle vector. The triangle class is in all of it's in many of the simulators, and this is just to create output. So this is just faces on the surface of the mesh so that you can create an OBJ output and then load that into Maya or something. And so it's a very, very simple class there. We have simulation parameters. All simulations have a set of parameters. Some are really common, like the time step. Some are specific to the type of simulator you're working on. So for spring mass, we have the time step. We have the total time that we'd like the simulation to run. We have the spring's stiffness constant, and we have the spring's damping constant. And then we have a output file name that for the name of the files that we should output. And then the object, the sort of, you could have many objects. The code sort of allows for that from the input file, but an object's going to have particles, springs, and the triangular faces that it will output. And then there's some code for I/O. We're not going to talk much about the I/O. We read an object, we read input files, we write OBJ files. Nothing too fancy there. Okay, so let's open the spring mass CPP file. So we include the header file, of course. There's no other includes necessary. We do define a floating point epsilon, so this is so that if something is small, we can say it's small and avoid dividing by 0. We have the parameters, we have a vector of objects. We read the input file, and that returns the parameters and the vector of objects. We start time at 0, we start our frame at 0. We initialize a double frame time to -1, and that's because whenever the frame time gets to 0, we'll output a frame and then reset it to whatever the frame rate is. So here we can see while the time is less than the total time, we'll run a loop and step through our simulation. The first thing we do is to check whether the frame time has fallen below 0. And I recommend actually outputting a frame before you do anything. Because if your simulator fails before it outputs even nothing, if your simulator fails before you have done anything, then that indicates one sort of bug. Whereas if it fails after it's done something, that's a different type of bug. So it's easy to find I/O bugs if the initial input is bad. So we print the file name that we're going to write. We write the OBJ file. We initialize frame time back to 1/30th of a second minus some small amount, and we advance the frame count. Okay, so here's our time stepping loop. Let's see, I can do this. We loop over all of our objects. We then loop over all of the particles in the object. We set initialize their velocities to 0. Then we apply gravity. And we're using the z direction as the gravity direction here. Y and z are both common in physics-based animation. Z is a little bit more common because z tends to be common in physics, and y is a little more common in computer graphics because we're used to images and projecting along the z-axis. Then we are going to do our spring forces, so we loop over all of our springs. We compute the distance in world space between the two particles that are affected. We then take the norm of that. Then we compute the difference in the velocities between our two particles. And then we compute our force. So we take Ks times the current length divided by the rest length minus 1. So that's our, between these two sets of parentheses, that's our stiffness, or our strain metric. And then we have our damping part. That's the velocity dotted with the direction of the two particles divided by the current length times the rest length and times d over L. And then we apply that force to the particle I and the negative force to particle j so that we have action-reaction. And then we loop over all the particles one last time. We check that we update the velocity using our Euler integrator. We update the position using our Euler integrator. And then we check for collisions with the ground, and if we do collide with the ground, we apply an inelastic collision, setting the position to be 0 and the velocity to be 0. So very, very simple. We can just drop things on the ground. And then we update the time, and we decrease the frame time. And so that's compiled now. I've already preloaded these into Maya. Oh, that's not a very good big window. What can I do here? Okay, well, it's going to be small. So here it is. Here's our spring mass system. And you can see that it jiggles a lot. It's probably a little too stiff. There's probably not quite enough damping. And that's a spring mass system, the simplest thing I can imagine doing. And we did it in a little over, well, how much code was it? 58 lines, minus the I/O, 60 lines. Okay, should we move on? I think so. Okay, so let's go back to that header file for the spring mass system. And we'll notice the differences between the two. So if you look at the particle class, there's actually no differences. We don't need anything more for a particle. For an element, though, versus a spring, we actually do define a convenience function, or sorry, we store the indices just like we did for the spring. We have the I and j. We store what we call a basis matrix. That's that matrix with the vector along the directions in rest space and then inverted so that we can easily compute the deformation gradient. And we store the normals because we're going to need those to compute forces. And then we define this convenience operator to get the indices out of the elements just to make the code a little bit easier to read. And then the triangle class is the same. The simulation parameters, instead of having ks and kd, we have lambda and mu because we can handle more general material models, and then we have our damping, just as before. And I think other than changing this to elements instead of springs, that's all that's changed. Okay, and then we can look at this. We have a little routine to compute the polar decomposition that actually just calls eigens SVD, and then we compute Q as U times V transpose, and that's so that we can compute the strain using the co-rotated strain formulation. Our initialization is much more complicated. So when we read in the mesh file, so when I created the spring mass input, I computed a bunch of rest lengths and I computed a bunch of masses based on the finite element discretization. And so I didn't need to do any initialization. But for a finite element simulation, we need to do a bit of initialization. So for each particle, we initialize its mass to 0. Then we loop over all the elements. For convenience and code compactness, we grab the positions of the elements' vertices. We compute normals, and you have to be careful when you do this if you don't copy this code, if you do it by hand, you want to make sure you're always getting outward facing normals, and that does involve a little bit of thought. We compute the basis, we set up the basis matrix being x1 minus x0, x2 minus x0, and x3 minus x0. We compute that basis matrix determinant, and we compute that basis matrix determinant because the determinant is going to be 6 times the volume of the element, and we're going to need the volume so that we can compute the mass. And then the mass is going to be that determinant divided by 6, so the volume, times the density, and then, that should be divided by 24, already a bug in my code. Okay, I will update that, but yeah, so we should be, we distribute that mass of the element over all of the particles, so it should be divided by 24 instead of 4 there. And then we invert the basis so that we can easily compute, so we don't have to invert it later when we're actually computing the deformation gradient. Okay, so that was initialization. This part's all the same, except we call the initialization for everything after reading it in. This part's all the same, the frames. This part's all the same. We apply gravity and initialize our force accumulators. This part's different. So here we, again, grab all of the positions and velocities for convenience and compactness of the code. We compute x, which is going to be the same thing we had for the basis matrix, except it's with the actual current positions. And then we multiply x times the basis, and that gives us the deformation gradient. We take the polar decomposition of the deformation gradient. We then we compute f tilde by taking the q transpose times f. And so this is going to be a symmetric matrix that was left over after we performed the rotation. It encodes the deformation of the object. Then we compute the strain as 0.5 times f plus f transpose minus the identity. And then we compute the stress as lambda times the trace of the strain times the identity plus 2 times mu times the strain. And then we do the same thing for the velocity component to get damping forces. We take x dot, which is the differences in velocities. We multiply that by the basis matrix. We then take q transpose times f dot. And then we take 0.5 times f dot plus f dot transpose minus the identity to get a strain rate. And we compute the stress rate in the same sort of way that we did for the lambda, except that we're multiplying by the damping forces. And then we compute the forces as q times the stress plus the stress rate, so the two stresses, times the outward facing normal divided by 6. And that divided by 6 comes from the same reason that we had, that the determinant is 6 times the volume and all the cross products and the math, and I won't bore you with the details. And then we update the particle the same way as before. We take the parameters times the dt times the force divided by the mass, and we update the position based on the velocity, and we do the same sort of simple collision detection. And so our finite element code weighs in at 121 lines, but conceptually it's not much more complicated. We had more complicated initialization, and then a little more work to compute forces, but conceptually not much more complicated than the explicit FEM. Okay, so let's look at explicit, open that header file again, and open the header file for implicit. How am I doing on time? Okay, need to pick it up a little bit, maybe. Okay, so here we have our particle. It hasn't changed. Actually, it has changed. We added a rest pose. I don't think I use that anymore. I think that was for debugging, actually. For the element, though, we did change things a little bit. We have to add the stiffness matrix that we're going to cache, and then we're going to have to store Q as we go along. So we computed Q before, but now we're going to keep it and store it in the element. And we didn't compute this stiffness matrix before. Remember that big matrix K in this big matrix equation? Each element has a 12 by 12, or it has 16 3 by 3 matrices that tell you about how how moving one node affects all the other nodes. And that's what the stiffness matrix is. And so we're going to need to compute that. We compute it once and cache it, and then we sort of update it as we go. Okay, so let's look at the code for that. So this is how we do implicit integration. We have our polar decomposition, we have our initialization that we had before, and then we have, oh, I did get the mass right in my implicit one. Go me. Okay, and then we compute the stiffness matrix, and this is the formula for the stiffness matrix. We go through and we get the normals, the opposite normal for I and the opposite normal for node J, and then we compute n transpose, and that's just an outer product between those two normals. That's happening here. And then we compute, we get a handle to that matrix, a reference, and then the stiffness matrix is going to be the lambda times nn transpose plus mu times nn transpose. And then we look at the diagonal and multiply that by ni, and then add that diagonal. And then in the end, we divide the whole thing by the volume. Or it's 36 times the volume. In order to compute the implicit integration, we have to solve a linear system. What that involves is applying in order to do that, we use something called conjugate gradients or any other iterative type solver. In order to use these iterative solvers, you have to basically be able to apply a matrix vector multiply. So this routine here, this method, applies the matrix A that includes K, that includes M plus dt squared K plus dt times damping, which you can see right here in the parameters. It applies that to whatever vector is passed in by conjugate gradients. So here's the part that computes M. We take the mass of the particle and multiply by whatever x is passed in by conjugate gradients. And then here we are applying dt squared k plus dt times d. And really what we're doing is we're taking the scale, which is taking into account the dt's. We multiply q times the stiffness times q transpose times x. And so this is what's called an element-free matrix vector multiply. It's very fast for small problems when you need a few number of iterations. If you have hundreds or thousands of iterations, you'd want to actually compute some compressed row storage sort of format for your matrix. But this is certainly fast enough for our purposes. Here are some routines that mimic routines that are available in CBLAS. So if you wanted this to be fast, you would use BLAS. But because I want it to be easy to compile on any operating system, I just wrote my own routines that mimic that. But DAXB is AX plus Y, and D dot is just a dot product for doubles, and it copies a vector to another vector, basic stuff. Here's where we actually solve our linear system. So this is conjugate gradients. I'm not going to go into too much detail here. We set a tolerance. We initialize iterations. We figure out the size of our system. We create sort of auxiliary vectors that we need in order to run the algorithm. The first thing we do is we do a matrix vector multiply and initialize stuff for the conjugate gradients. And then there's conjugate gradient iterations, and when it's all done, we have a solution. And yeah, so this is not preconditioned conjugate gradients. The obvious thing you would want to do if you wanted this to be fast is precondition it. And then the rest of the code actually looks pretty similar to what we saw before. We initialize our objects. We do the same thing with the frames. We do the same thing initializing our particles. Here, instead of computing forces, what we're actually computing is the right-hand side. And if you remember, the right-hand side had no damping term. It only had the stiffness term. And so, or it had no damping forces. It only had the elastic forces. And so this is only computing the elastic forces, and we are caching Q here. And then we set up our integration by setting B to be the right-hand side that we're computing, and then X is going to, our initial guess for conjugate gradients is just going to be the current velocity. We call solve, we set the velocity to what the solve returned, and then we update position just as before, and then our collision detection and everything else. And so now we're weighing it in 100 lines more, so we're at 211 lines. Okay. And we're 5:06. I have to make the decision, do I show you fluids or rigid bodies, do you think? Demos, that's even better, okay. Okay, so let me hide this one. This one I'll hide. Okay, so here's, let me do this one first. I'm showing them to you all at once. Okay, stop, go back to the beginning and play. Sometimes this is picky. Okay, so this is explicit integration. You get a nice little bounce. We're not doing elastic collision, so you don't get a very big bounce, but you do get a nice little bounce. It's nice and stable because I've chosen the time step and material properties so that happens. If I increase the time step or made it more stiff, then we would definitely see explosion like Tamar showed you earlier. So let me stop this and hide. And then with implicit integration, did it not? Okay. You'll see that things are much, much more damped, and that's because that's just the artifact of linear and implicit Euler. In order to remain stable, it reduces the energy in the system. And so we don't get as nice a bounce, but you're much more likely to remain stable in most of the circumstances you're interested in. You also get less deformation. I mean, it almost looks rigid. And I can show you rigid, so there is a rigid body simulator in there, and it goes, didn't unhide. So this one has elastic collisions with a coefficient of restitution of something like 0.8, so you get this nice big bounce and jiggling and bouncing around. And then the fluids I have to show you with my special viewer. So, and out. Or do I not have the? Let me real quick run fluid. Well, it won't be real quick because this is slow. So the fluid is the slowest of them all, and I'll show you a little bit about how it works, though, while we're waiting. So we have simulation parameters. Things are more complicated here. We have the total time. Now we have a density. We have the flip ratio. Oh, I'll tell you about how the fluid how this works. Okay, so we talked about the various models, but we didn't actually talk about how you write a fluid simulator. So what we typically do is what we call operator splitting, where we first compute this U star solution, which is going to be UN plus delta T times the advection term, and then the viscosity term, and then the external forces term. And then we'll compute UN plus 1 as U star minus the pressure term. And then the obvious question is, what is P? Well, we know that, so this is just the equation we had before. UN plus 1 is U star minus the pressure term. We know that we want un plus 1 to be divergence-free, so divergence of un plus 1 should be 0. Plugging that in, we get that the divergence of u star minus gradient p should be 0. And then if we use the associative rule to distributed rule on the nabla there, we get that the divergence of u star minus the Laplacian of pressure should be 0. And pulling on to the other side, we get that the Laplacian of pressure is rho times nabla, the divergence of u star. So what we do is we first update u star in time using all the forces that are simple to compute, and then we do a big pressure solve to make sure that it's divergence free. And so when we do flip, we advect using particles, then we do a particle to grid transfer, so we have velocities on the grid. We then compute external forces, velocity, and boundary conditions. We compute the pressure and update the grid velocities, and then we do a grid to particle step to update the particle velocities. So this is one of those methods that I talked about that is sort of a hybrid. Okay, and now we've written all of our fluid files, and so we can do particle view fluid dot %03d dot part, and with any luck, that opens up and runs. And so this is a simple basic flip solver. It's nothing terribly fancy. But you can see that it gets fluid-like behavior pretty well. And the second time it plays through, it'll be faster because it's currently loading the files. All right, so I think maybe we should go ahead and stop there. And if you actually have any questions about any of the simulators, feel free to email me. I'm happy to maintain them and fix bugs and whatever. Thanks for coming. I hope you learned something. Oh, I guess we could ask questions, right? There's 2 minutes left. Anybody have a question? No questions? All right, well, enjoy the rest of SIGGRAPH. And I'll do a final plug. There's a Frontiers talk tomorrow at 8 a.m. on metric telepresence. It should be good stuff. And enjoy the rest of SIGGRAPH. Thanks.